Dean Sciences Shri Guru Tegh Bahadur Khalsa College, Shri Anandpur Sahib. Over to you, ma'am.
Thanks, Dr. Mandeep. Good morning to all delegates. This session is on integrated. Thanks, Dr. Mandeep. Good morning to all delegates. This session is on integrated approach on science and technology for sustainable future. I will give brief introduction. This session is organized to provide the greatest attention to the need of the hour to integrate all the science and technology people and attain the sustainable growth in the manner that would not harm a coming generation future. The theme is matching with the National Science Day theme of India and is also being partly sponsored by Punjab State Council for Science and Technology under the NSD 2022 celebration program. The integrated approach of all branches of science is very important for humanity, as we have seen this in the COVID-19 pandemic time. It is also very crucial to disseminate and communicate the scientific knowledge to our younger ones so that they could really grasp it at early ages and be a part of the glorious journey of human growth and revolution sustaining our environment, our livelihood, human life, and its value. I am excited thoroughly to share that the session will be chaired by Dr. K.S. Bath, Joint Director, Punjab State Council for Science and Technology, and the audience will be enlightened by the thoughts and the work of many prominent scientists of this area like Dr. Narinder Singh, Dr. Arvind Gupta, Dr. Pushpinder Pal Singh, and Dr. Yashveer Singh from IIT Ropar. In the end of this session, we will be getting an opportunity to interact with our eminent scientist, Desh Bhagat Sardar Lal Singh, Oration Lecture Awardee, Dr. Adarsh Pal Vijji, who will enlighten us with their wonderful words. Now, I would like to hand over the proceeding of this session for the formal welcome of all the dignitaries and delegates to Dr. Mandeep Kaur. Thank you.
Thank you very much, ma'am, for the brief overview. It is a great privilege for me to introduce Dr. Kurbir Singh Bath, the Joint Director of Punjab State Council for Science and Technology as the chairperson of the session. Dr. Bath has completed his doctorate in environmental sciences from Punjabi University, Patiala, on the research topic Aquatic Ecosystem and Limnology of the Punjab Wetlands. Since 1998, Dr. Bath has been serving as the Nodal Coordinator of Department of Science and Technology, Government of India and Government of Punjab. In addition to heading the STI Outreach Division, he is the State Coordinator of Children's Science Congress, National Science Day, National Mathematics Day, Green Corps Program, and Swachhta Action Plan. He has 9 books, 35 research papers, and 50 journal articles to his credit. I owe you a warm welcome, sir. It's a great pleasure for us to have such an eminent personality among us today. So
Thank
with
you
your
so
permission,
much.
sir, maybe start the session.
Yeah. Please start. Please go ahead.
Thank you very much, sir.
Yes, thank you.
For the very first invited talk today, we have among us Dr. Narinder Singh, Professor, Department of Chemistry, Indian Institute of Technology, Roopnagar. Dr. Singh has completed his doctorate from Guru Nanak Dev University, Amritsar, and has been a postdoctorate fellow at Osaka City University, Japan, Yonsei University, Korea, and Robert Gordon University, Scotland, UK. Since his joining at IIT Ropar in 2009, where he has served as the department coordinator for a tenure of almost 3.5 years, Dr. Singh has completed various national and international projects. His major area of research involves the organic synthesis of supramolecular assemblies and evaluations of their photophysical properties for sustainable development, in which he owed projects including consultancies worth crores. He has published 285 research papers in international peer-reviewed journals. Through his able guidance, he has produced 12 doctorate, 5 postdoctorate, and several MTech students. For his excellent contribution in analytical and environmental chemistry, Dr. Singh bagged the prestigious Professor S.S. Sandhu Medal by Indian Chemical Society and Faculty Research Innovation Award by IIT Ropar. We feel indebted to you, sir, for your presence. I now invite Dr. Narinder Singh to present his talk entitled Potential Nanomaterials for Chemosensor Development and Water Purification.
Yeah, thank you very much for the invitation and for the introduction. And let me share my presentation. Yes, can you see my screen?
Yes, sir.
Yes. Okay. So, as the theme of this conference is sustainable development, and I think students, participants, they know the sustainable has one meaning, that is, if we do something today, some development, anything, and it will not harm our future generations, then it's a sustainable. Means any development with some accountability is a sustainable development. If we make a technology or any development which will affect our future generation, then it's not a sustainable. Oh. And time is the bit. There were several technological revolutions. Please wait on the mic. Everybody mute the mic. So I was saying time was a witness that in the country there were several development which has affected our natural resources, flora and fauna. And that's why we need a strategy where we develop the things. And I have taken into account two topics, that is chemosensor development and water purification, for today's discussion. If you see my research activities, I have done work in sensors to develop to determine the toxins in soil and water. And whenever we know, okay, these type of toxins are present in the soil or in the water, then we devise some of the strategies for remove those type of toxins. And some of the things which we have already done, that is removal of metal ions from the industrial wastewater, we have already suggested to several industries. And finally, wealth from the waste means it may possible that some of the material which are at the moment like a metallic particle, they are present in the water samples like nickel or chromium. They are present in the hand tool industries, pollutant of hand tool industry. What you can do, you can convert those material into nickel nanoparticle and chromium nanoparticle or alloy nanoparticle, and after that you can utilize those in boilers. So that is one example of wealth from the waste. Another thing which we have completed just now, although it can also be a part of sustainable development, that is we have made the plastic from the rice straw. Now, the first topic, the chemosensors. Whenever we are talking about the chemosensors, we must be having two parts. One is a recognition part, and this is receptor part. Another is you must be having some readout. And receptor is receptor subunit has some binding site, which has compatibility, great compatibility to type of analyte. Like if I talk about a complex mixture, like this is a complex mixture. This is complex mixture. You may take a water sample, industrial-based water sample. Now, out of that complex mixture, let us say you want to analyze the nickel. Then I have to arrange the stereo electronic parameter in such a way that whenever this nickel will bind here, and after that there will be change in the signal. And if any other analyte is coming because of its shape or orientation or conformation, it will not give the readout whatsoever is expected when the nickel will bind. Then it becomes a sensor. Means I need a selectivity over here, and and it should not be so
So you're not audible.
color change. It's not audible.
Excuse me, sir.
Yeah, just a minute.
So you're now audible.
Not just a minute.
So it's audible now.
It's audible.
Yes, sir. Yes, sir.
Okay, okay, just a minute. I continue. So I think I will be audible now completely.
Yes, sir.
Okay. So I was talking about the selectivity and the sensitivity, and so these are the three we take into account whenever I am working with the chemosensors. Although there can be many more, but I have concerned with these. Today I will discuss first two. Now, when I joined IIT long back, around in 2009, at that time, I want to develop a system which should have some of the background whatsoever I did in my PhD or postdoc, but it should be a new, it should not be a replica of the same. Then I thought, let me start with the research career in the field of biodiagnostics, or the second field I was selected at that time, that was environmental analysis. However, if either I start with biodiagnostic or environmental analysis, in both the cases, the analysis need to be in aqueous medium and in the water system. However, whatsoever sensors was there reported at that time, most of the sensor was like this, whatsoever I have shown. And after that, I have published a couple of review articles in this area. Now, those who are from the chemistry, they can very well say, okay, if we have this type of receptors, these type of receptors, because of this aromatic character, they are not soluble in water. They are not soluble in water. Now, this analysis has to be performed in the aqueous medium, but these sensors, they are not soluble in water, and sensor I need of this type. Then what to do? Then we thought, I have taken basically that idea was conceived from one of the person in the pharmaceutical industry. he said that there are many pharmaceutical ingredients, APIs, which are not water soluble, but still they are in the water in the form of some nanoemulsion, in the form of some nanoparticle, organic nanoparticle. At that time, inorganic nanoparticles, they were quite abundant in the literature, but organic nanoparticle was not that abundant in literature. Then I thought, let us start with organic nanoparticle. And we struggle, in the initial career, early career stage, everybody has to struggle. And nothing was new for me. I struggled for these type of organic nanoparticle. Uh, Most of the time, I was not getting the reproducible results. Then we realized that most of the time I am getting the nanoparticle along with these type of agglomeration. So these agglomeration was causing the non-reproducibility in the results. And eventually we remained successful to make this type of nanoparticle by making solvent composition. Solvent, first thing is the solvent choice, composition, injection time. So these were the three parameters which we have to take into account at that time. How that was there, how a material like this, which is which is expected to be a lipophilic character, hydrophobic character, how this is now soluble or suspended in the water system. Then what we did, this material was soluble in DMSO, DMF. We have dissolved in 1 ml of DMF and injected this into 99 ml of water. Now the beauty is DMF is soluble in water. This compound was not soluble.
So your speaker is muted. Sir, your speaker is on mute mode.
Yeah. Now
Sir, it's now audible.
can you listen me? Just a minute. I'll switch off all of this.
Sir, it's audible
Okay.
now.
Now I think you can listen. Okay. So I was saying that we have to make a choice for synthesize this nanoparticle by using DMF I have taken here, and 1 ml of DMF I have taken and put this material into 99 ml of water, and after that we got these type of nanoparticles. If we have this type of agglomeration, then probably you will not get the nanoparticles. So this was suspended over here, and after that, if you take contaminated water from any river, and if that river water contain mercury, and you put 1 drop of that one, immediately the color will change to pink. And even you can take the food grains, you crush those food grains, and after that make the digestion, and you have a sample, you put 1 drop of that one, you will get the color change. After that, what we did here, everybody said that for this type of things, this type of nanoemulsion, you need a skilled manpower. And if you want to give this to a municipality, to a common people to analyze the things, so probably they will face the problem. Then I coated this compound on the silica. However, here shelf life was not good. Then I put the same material in polymer matrix. This is polymer matrix. And here the shelf life is up to 6 to 7 months. We have seen under room condition, room temperature, and normal humidity, it was stable. So this was one thing which I achieved long back, almost 10 years back. And after that, the synthesis was the challenge over here, because those who know the organic chemistry, they can say that this molecule is challenge to synthesis. So that's why we shift our plan to another type of sensors where the synthesis is easy. Here, how the synthesis is easy, you take just beta ketoester, you take aldehyde, and you take bench thiazole, mix them together and reflux for recommended time, and after that you will get the precipitate which are pure this compound. You just recrystallize and you will get the pure product. Very easy. And if you have this compound in your hand and you can do the mercury analysis, you can see if I add the mercury, this here the absorption is decreasing, here the absorption is increasing. However, the fluorescence intensity is quenching. And but in fluorescence spectroscopy, those who are dealing this fluorescence spectroscopy, they know that this type of signal death is not a preferred thing. Diminished signal is not preferred. Always your signal should generate, although you can do the analysis, but for practical or industrial or commercial purpose, this signal generation is important. Another thing is, if I treat this sensor with chloride, then you see if you titrate with mercury in this way and reverse is there whenever you have chloride. It means if your sample contain the chloride, then again this material is not so good. One is ratiometry, another is if you have background of chloride, then probably this will not a good choice. And how we address this thing? For ratiometry, what I did, I have taken this compound, and after that we coated this material on nanoparticle, zinc oxide nanoparticle. And after that we have seen that this is for your this receptor sensor system. And if you add the mercury, then there is a remarkable change in the fluorescence signature. While for other metal ion, we don't have that type of change, that type of shift in the wavelength. And here we have the ratiometry. And if I take the wavelength intensity at this wavelength versus over the intensity at this wavelength, I have got the straight line. So good for, this was almost good for commercial purpose. Then the people said that if we have handheld device, then it will be having more value. Then let us do more research for getting some handheld device. So again, we have started with one of the compound, made their organic nanoparticle. These organic nanoparticles are quite stable. The color of those organic nanoparticle is, you can see red. And the moment you add mercury, the color is changing to the yellow. And if we take the samples from river water sample, we take pond, we take tap sample, or we spike with the mercury, we have a linear concentration. So this thing is very, very important. If you don't have a linear dynamic range, you can see the dynamic range is quite good. 0 to 40 micro, 0 to 40 micromolar concentration it's detecting. Quite good linear detection range. And error bar you can see very negligible, very small error bar are shared there. So means the reproducibility is very, very good over here. So then I was excited, let us make a system handheld device. So we made a simple slot here. Battery we have here, the LEDs we have here. After that, put that sensor strip. This sensor strip will be put here. You add 1 drop of water, and if there is a mercury, if you have 5 nanomolar mercury, color will be like this. If you have 20 nanomolar mercury, color will be like this. Take photograph from this camera, and after that, break those pixels, and you will get the concentration of linear concentration. If I take the green pixel and linear concentration, I will get over here, and you can see here change in the metal concentration, like from 0 mercury to 20 mercury, you can see the difference in the photographs. That is first, as I said here, the first thing is you need a linear graph in the spectroscopy. Second thing is your film, that sample strip or your film should be such that if you change just 1 nanomolar, immediately the color change will be very predictive, like we have shown in these photographs. So we were quite happy with this type of thing. But the major thing is now if you change the camera, like you have calibration with one camera, and again you change this camera, means you change the mobile, then again you have to do the calibration, and calibration can be a tedious process for somebody. Even we try to develop the mobile app, but again one has to calibrate the thing. If calibration go wrong, everything will have some meaning. So this is one thing. And then we thought, let us do some more research and make a system like this. Here you strip here. This is our our lab has made this system. UNO based RGB based system. Here we have excitation source. Here we have detector, and you put shine light here, and after that you will get the RGB value of RGB over here. And after that you will get the RGB, and you can also train the system to give directly the mercury concentration. Purposefully I am taking only one example, mercury. We have sensor for everything almost. For any anion, cation, biomolecule, we have done extensive research on this area. So after that we had future projection. As you have seen that once I publish one paper, after that I have one question, how to proceed further. Then one thing was on-site testing kit for multi-analyte, means pollution board. If let us say pollution board people, they are going to some factory, or food inspector is going to a factory or that sweet shop, they take the food sample and put in that way in that multi-analyte sensing array. After that, he or she will get the whole testing. One was this stream. And for this, we get the funding from central government. And second dream was real-time online monitoring of water samples from river water. This dream is fulfilled by Punjab State Council of Science and Technology. They have given this project, and last week we have shown them the working of our online monitoring system in the lab, and now we are going to demonstrate it in the river, and after that we will install this one. Third is there are several protocols which are there, BIS approved protocols. But I want that for some of the analyte where we don't have BIS approved protocol, my dream is IIT Roopad may develop those type of protocol which is approved by BIS, and it become a gold standard in the country. This is my third dream. So you can see this dream we are completing. This 90% we have completed, and this is still a dream. We have not done anything in this area. Now, food. If I have to say about this one, food, let us talk about food. So, as far as food is concerned, sometime what happen? If meat sample, you take a meat sample, you take a vegetable which is enriched with the protein, and after that you see if there is a change in the color, like there is a degradation, spermine and spermidines are formed, and we have kept meat samples over here, and this distance is almost 2.5 centimeter. And if the meat is degraded, there is a change in the color, and from that change in the color, I can say, okay, meat is degraded or not. And we have made an envelope, and now last I think in the month of November we have shown this and went to the participants, or 30 participants we have trained in this area, contamination free food packaging, and we have shown that envelope to those participants. And I think how much time I have? How much time I have?
5 minutes.
5 minutes. Okay. So then I can skip some of the. Now this is another thing which we have done, means multi-analyte. So for multi-analyte, we have made a pattern-based recognition method, and where we have, if we have, let us say, uh, 10 analyte, 20 analyte together, that we can analyze, which we have published, and we have technology ready to give to the industry. You can see here we have taken 7 or 8 analyte, and after that we made a strategy, pattern-based recognition strategy, where the different analyte behave differently, and we get this type of data set. And for after this data set, we got the this type of pattern, and this is called the simultaneous estimation of the analyte. And this type of LDR array we have made. In that LDR array, you can put 96 samples. 96 pellets are there, and at one time you can put 15 to 20 samples together, and after that you will get the array. This system is our ready system. Now we are going to transfer this technology to an industry. Demo device I skip. And another projection we have working on the theranostics, where our sensors are detecting as well as doing the therapy over there, and killing of MDR bacteria, and alternate to benzyl choline chloride. We remain successful in this area. During the time of COVID, we made some of the formulation which was given to 6 different industries for commercial production, and at the moment they are producing in a large extent. And these formulation are non-alcoholic and non-volatile. And now we are finding some alternate to benzyl choline chloride, and I am happy to tell you that one of the company has already taken up technology from us, and now animal trial is complete, and if they have funding, they will go for the human trial. So this is another projections. So I think I skip these slides. Just I gave a brief introduction, and after that I skip these slides. Like cancer diagnostics, we have done gauze for bacterial infection. For the treatment of bacterial infection, we have developed this organophosphate detection and degradation. We have developed. This is degradation, pesticide degradation. You know, in Punjab, there is extensive use of chloropyrifos. People are using, and they are there in the vegetable. We have the formulations. If you treat it, those pesticide-laden vegetable with our formulation, it will degrade those your DCC and chloropyrifos, and after that the material will be safe for the human consumption. So this is all about whatsoever I have we have done with the help of my students and postdocs, present student and the past students. Thank you very much for giving me an opportunity to interact with you. And if you have any question, please let me know.
Thank you so much, sir. Any questions from the audience? Thank you so much, sir, for an imposing lecture. The insight provided by you in the field of chem sensors is commendable. It will be of great importance for young chemists for the research findings. Thank you so much, sir, for your wonderful lecture. Heading forward for the second invited talk of the session, that is modeling of non-equilibrium stochastics transport. I take the privilege to introduce Dr. Arvind Gupta, Associate Professor and Head of the Department of Mathematics in the Indian Institute of Technology, Rupnagar. Dr. Gupta has completed his master and doctoral degree from IIT Roorkee, after which he joined Birla Institute of Technology and Science, Pilani, in 2006 as an assistant professor in mathematics groups and later in 2010 joined Department of Mathematics, IIT Ropar. Dr. Gupta's areas of research interests include mathematical modeling of traffic flow, asymmetric simple exclusion process, lattice hydrodynamics, and cellular automata. Dr. Gupta has more than 100 research publications in reputed journals. He has successfully completed the DST, ISRD-sponsored research projects and guided 3 PhD students. Presently, Dr. Gupta has 5 doctorate and postdoctorate fellow in his research group. We are very thankful to you, sir, for gracing our occasion. Dr. Arvind Gupta ji, over to you, sir.
Thank you very much. Good morning to all. I'll start with sharing my slides. Is my screen visible to you?
Yes, sir.
Sure. Fine. So thank you very much for giving me the opportunity to talk about what I used to do and what I have done during the last 10 years. So the title of today's talk is Modeling of Non-Equilibrium Stochastic Transport. So I'll try to briefly discuss about each and every component of the title, and then I'll try to talk about what basically we do. So transport, as the title is stochastic transport, so I'll first try to explain what is transport. So transport is a natural phenomena which is seen almost everywhere, right? And one can simply say this is nothing but a signature of life. So if there is some sort of transportation, we can simply say that someone is alive. Otherwise, yeah, that thing is not alive, right? So this transportation happens actually in natural systems as well as man-made systems. So I'll try to firstly brief about what type of natural systems or man-made systems we have seen. So we have seen transport of vehicular traffic, where all the vehicles moves on road, or basically human traffic, which we call it as pedestrian flow. And we have seen all these things in our daily life. This sort of 3 examples gives you a feeling about the natural transport. So the first one is this ant tailing in the desert, where you have seen that the ant moves and follow a certain path by doing some biosensoring or some chemical, but definitely there is some sort of a transport happening by ants in the desert. We have also known that a neuron cells basically transmit informations from one place to another, and this is once again can be thought of some sort of a transport. Third thing is like the birds flying in the swarm, like a large collection of birds. When they flow together, they actually make very beautiful structures, and maybe the number may be large enough, like 1,000, 10,000, or maybe bigger than 10,000, and they actually moves in such a way that they never collide. So the important thing is, if we will try to compare our vehicular traffic or the systems, which man-made systems, with natural systems, what we have realized that in our man-made systems we have seen traffic jams, accidents, and various other things, but this generally never happens in these natural systems. If it happens, definitely that leads to catastrophe, and it is bit difficult to actually handle. So now the task is, can we understand the transport in natural systems and can mimic this sort of understanding for developing our man-made systems, right? So this is very, very essential for industrial development and sustainability. So I'll try to first focus on one particular transport, which basically is known as transport of molecular motors. So I'll very quickly give you a brief outline about how biologically it happens. So let's take a eukaryotic cell. So this is some sort of a eukaryotic cell, which is having a nucleus, and basically outside there is some sort of a microtubule network, right? So these green lines, they are some sort of an highways, and they are all connected with some nucleus, fine. So if I'll try to make a cartoon of it, fine, this is not actual picture, this is some sort of a cartoon, just to understand what is the important ingredients for our study. So we have a cell, we have a nucleus, fine, and outside this nucleus we have actually this purple color highways, and these purple color highways can be thought of like national highways, fine. And there are also smaller scale highways like this, which we have shown it here through this yellow color marking. So they can be thought of as an state highways, fine. So here I am interested in this purple color highway, or I should say national highway. So they are known as microtubules. Over this microtubules, different kinds of molecular motors, or we can say motor proteins, moves. Few moves from nucleus to outside, and few moves from outside towards nucleus, fine. And the important part or important role of these motor proteins is to carry information or transport important ingredients or material from nucleus to outside of the cell, or outside to towards the nucleus. So here I have shown you actually three important class of motor proteins. One is kinesin. So this is a kinesin, and we have a dynein, we have a myosin. So there are variety of molecular motors which actually do the thing. So these different kind of motor proteins can be thought of something like a truck, bus, or maybe smaller vehicles, fine. So essentially this sort of transport is stochastic in nature, and this happens basically in a collective way. So the idea is different molecular motors moves over this highway and transport important ingredients. Very quickly, let's see what type of thing happens. So here we have actually two important players. One is the road, which we say cytoskeleton. So this cytoskeleton is the collection of this microtubule. So it's a network of microtubule. And another one is molecular motors. Fine. Even this cytoskeleton, we have three kinds of cytoskeleton in general. One is actin filament, which is in like 0.7 nanometer, which is the smaller scale, like general roads. Microtubule is little bit bigger, and which is of scale 24 nanometer. And we also have an intermediate microtubules, which are some sort of 10 nanometer. So here in this discussion, we will focus on this microtubule, which are little bit bigger size of cytoskeleton filaments. So the structure is actually there are alpha beta tubulins, and if you actually collect this 13 to 14 this alpha beta tubulins and make it some sort of a ring sort of structure and connect these rings sort of structure, so this becomes some sort of a helix, and this helix actually is nothing but the microtubule over which these molecular motors moves. Fine. So maybe I can show with the help of a small cartoon how does it happens. Fine. So we have some sort of a structure, and this molecular motors. This is a kinesin having two legs, so it moves carrying a cargo. This cargo is nothing but amino acid, and they transport information from one place to another. Fine. And once again, try to understand, they are at the nanoscales. Fine. So somebody can thought of like, I'm trying to compare nanoscale transport in natural systems with 2-3 meter vehicle transport on road. So let's see whether what can these nano sort of transport can do. Fine. So this is a picture of cuttlefish. So try to very quickly visualize what does it do. So this cuttlefish actually controls the pigment in his body, and the idea is whenever he or she feels actually some danger, it tries to match its body color with the background so that it becomes like imaginary sort of thing. Fine. And that means this cuttlefish is having an ability to control the dynamics of molecular motors inside the cell, through which this can achieve this sort of color changing. Fine. Now, in 2016, three scientists, Sauvage, Stoddard, and Faringa, they actually try to develop this sort of molecular motors, which without even taking the energy can actually move in their lab, and they were awarded Nobel laureate in 2016. So the aim was that these three try to develop this sort of molecular machines in their lab. Right? Now let's try to very quickly see what is the properties of molecular motor proteins. So roughly motor proteins is having velocity which is ranges from 0.01 to 100 micrometer per second, and they move linearly. Fine. They took one step which is of range 0.3 to 40 nanometer. Why I'm giving this range? Because there are large variety of molecular motors, so which ranges from the step size ranges from 0.3 to 40 nanometers. So once again, it seems to be very small. They exerted a force which is in petanewton. The fuel, the energy which they consume is from the hydrolysis of ATP to ADP, and the important part is they are highly efficient. So majority of them are efficient where efficiency is more than 50%, and the power is like jet engine. So the question is, the velocity is very small, the step size is very small, they exerted a force which is once again very small. So how will we compare it with actually our vehicular traffic? Fine. So if I'll just very quickly try to compare the most efficient engine known on earth made by humans is the Honda Accord, which is having efficiency of only 10%, whereas all the molecular motors are having efficiency which is more than 50%. So that means still man has not made any engine which is at least comparable to the naturally made systems. Fine. But when we'll see, try to visualize the velocity, step size, and force, it seems like we are not these molecular motors things are not comparable with the vehicular traffic. So let's see, try to compare it. So if I'll see the size of a motor protein, this is of 10 to the power minus 8 meter, whereas our automobile engine, if I'll even choose the smallest one, is of at least 1 meter. In the case of kinesin, the fuel is addition ATP, and for our engines, they took hydrocarbons. Right? If you try to see the speed, it is 3.6 10 to the power minus 3 meter per hour. So 10 to the power minus 3, and here we have roughly 120 kilometer per hour, or 1.2 into 10 to the power 5 meter per hour. This sort of engines. But if I'll try to compare the speed with respect to their length, so if you see it, if I'll try to find out the speed of the kinesin with respect to its own length, it is 3.6 into 10 to the power 5 length per hour, whereas our automobiles are lesser than their speed, relative speed. Fine. So that means if I'll try to see their speed with respect to their own size, it is much more than what we have in our hand. And the work efficiency is no doubt much more than what we have for our automobile engine. So that means, yeah, we can compare we can understand the natural made systems and the dynamics happening inside the systems, and can develop or can utilize the understanding for developing our vehicular infrastructure. Fine. So now I'm moving towards the mathematics part of it. So generally, if we need to understand any concepts through mathematics, we try to model it. And broadly speaking, model can be of two kinds: microscopic or macroscopic. So microscopics are those kind of models where we try to understand the characteristics of individual things, whereas macroscopic are those where we try to aggregate the individual characteristics and try to understand the behavior in a global level. Fine. So here, since we are understanding, we are not interested in individual vehicle, we are interested in the whole traffic or whole dynamics. So we will be opting for the population-based model. But definitely, this individual-based model is also useful for some other purposes, but which we are right now not interested. So let's see how one can actually model the whole thing. So we have two scenario. We have a microtubule where this molecular motor moves. Let's assume the simplest case, they move from left to right, and they do not change their direction or something. Similarly, we have a road where these cars or buses, they are moving in a unidirectional way. Fine. So both the motions, they are stochastic in nature. Why? Because somebody can increase the speed in between or decrease the speed, or there may happen various other uncertainties which we are not as sure. So what we can do, we can actually represent either this microtubule or a car through a particle. So this road is represented by a lattice. So lattice is having some sides, right? And we have a circular thing, this cell. This represents either the molecular motors or a car. So this sort of representation in physics is given a name which is known as totally asymmetric simple exclusion process. Why this name? I'll just very quickly tell you. So totally asymmetric because all these circles or all these particles are going to move in one direction from left to right. The rules of transportation is simple. Let's say if you have a circle here, this circle can jump to the next, or this particle can jump to the next side if the next side is empty. This side, this circle cannot jump to the next side because this next side is filled. So the rules are simple. That's the reason totally asymmetric simple. Exclusion in the sense like because a site can have only one particle at a time, cannot have two or more than one particle at a time. So that is the reason exclusion, and this is some sort of a process which is going to occur with respect to time. Hence, the name is given as totally asymmetric simple exclusion process. Fine. So now I have moved from the motivation from coming from the biology towards physics, and then I'm jumping towards mathematics. So this TASEP single channel model, I'm just explaining what is this. This was introduced in 1968 by McDonald, and he was interested in studying the kinetics of biopolymerization. Fine. So the idea is once again same. You have a road, or which is represented by this lattice. You have a particle distributed over here. These particles are randomly distributed, and the particle cannot jump if the next site is filled. The particle will jump with the probability 1 if the next site is empty. And since we have an open system, particle can enter with a rate alpha from here and can leave the system with a rate beta. So if we can solve or understand what is going to happen in the steady state here in this lattice, then we can actually understand the dynamics and then later on we can club more complex dynamics here and can understand that transportation process also. Right. So first thing is how to solve this simple system and find out the probabilities in steady state. Right. So we'll quickly jump to a case where we have a periodic scenario. Why? Because here in this case, this alpha and beta are two additional things. So let's try to first solve without this alpha and beta. So what is the best way? You connect this last side to the first side, right? And then in that case, you will be having a periodic TASEP. So periodic TASEP is if you have, let's say, particle here, the particle will jump and then they will keep on jumping with the simple rule. If the next site is empty, they will jump. If the next site is filled, they will not jump. Fine. So now the question is, if let's say if I am having 1,000 sites and 20 particles, and I will allow them to move, what will be the configuration after long time, or maybe steady state distribution of the particle? So this problem was solved by Derrida and his group in 1993 and another paper in 1999. And what they said, let's write down the master equations governing this flow. So how to write down the master equations for this? It's simple. What you can do, you can actually talk about tau I. So this tau I is a distribution, Bernoulli distribution, which takes the value 0 or 1. So when it is going to take the value 0, if the particle is not there, the value is 0, otherwise the value is 1. And what is this I? I is nothing but the numbering of the lattice. So I equal to 1, 2, 3, 4, 5, and so on. Right? So now I'm interested in how the statistical average, this symbol represents the statistical average. What is the rate of change of the statistical occupation number, tau I? Fine. So once again, this is very easy to obtain. We have a gain term and a loss term. So this is the master equation which can give the loss and gain term. Fine. So it's not difficult. The idea is if you have a particle at I-1th site and ith site is empty, particle will jump. Otherwise, there will be nothing. Living thing is if you have a particle at the ith site and I+1th is empty, the particle from ith site will jump to the I+1th site. Hence, you got this equation. Fine. This equation can be solved by various ways, which was presented by Derrida and Evans in their papers. And they found that in steady state, we are going to have a uniform distribution. Right? What is uniform distribution? So the idea is, let's say if you have 1,000 sites and you have 20 particles and you have randomly distributed these 20 particles here, and then you are allowing the system to run as per the simple rules, then later on, the particle will be equally distributed over this lattice with the density 20 by 1,000. So they compute the density, which is given by the number of particles divided by the total number of sites. So this was the solution. And once again, if you recall, it took almost 20 years to solve mathematically this problem. Because if you see, MacDonald introduced it in 1968 and the solution came in 1993. Earliest solution came in 1993. Fine. And if we'll try to see the theory part with its phase diagram, so we have three different possibilities. What are the three different possibilities? If you recall here, we said density is n by L. So now if I'll fix my L, I can vary my n. So n can vary in three ways. If my n is more than 50%, so here this is versus n versus the density. If the n is less than L by 2, then we have a low density phase. If it is exactly L by 2, we have a maximal current phase. And if it is more than L by 2, we have a high density phase. So this is the simplest result which Derrida has produced. The notion of this LDMC and HD phase, low density, high density MC phase, is very easy to understand. If I'll plot current versus density, so this is going to be the plot, which is convex sort of function. So here it says that if density is less than 0.5, the current is going to increase. So if the current is going to increase, we call this phase as low density. The maximum value is achieved at exactly 0.5, hence we call it as maximal current phase. And if the density becomes more than 0.5, the current is going to decrease. So we call it as high density phase. Fine. So now once again, we can actually mimic this thing with the traffic phases. In traffic, vehicular traffic, we have seen the normal situations where if I'm driving with some speed and I want to increase my speed, I can increase. That means I'm in low density phase. The maximal current phase is more useful for optimizing the flow, whereas high density phase can be connected with the traffic jam sort of situation. Fine. So these three phases are once again are having connection with the three important phase differences of water, solid, liquid, solid, and gaseous states. So they can be easily connected to that part. So once again, now I'm jumping. So if you recall, we started with an open systems, and the reason of open system was because we have a control strategies. How? So we have a, let's say, a road. So I can keep either a traffic light or maybe some restrictions on the speed from here and here, such as I've shown it here. Dispatch, you can have it at max 10 km per hour, or dispatch you can have 15 km per hour. So this sort of speed controllers can be installed, or traffic light can be installed to control the dynamics. Fine. So in order to understand this, we have to solve this open system instead of closed system. So in open system, we have the same lattice, but now I have an entry with the rate alpha and exit with the rate beta. So this alpha and beta are two additional features which I need to incorporate in order to understand this open system. And open system seems to be more realistic for the application part. Fine. Now I'll once again try to develop the model using the same approach. So the master equation is going to be the same, exactly the same for the closed. Only we have two boundary conditions because of this incorporation of alpha and beta. So we have an alpha, so at the left hand, so we have tau 1 is this first site, So tau 1 by dt having the role of alpha, and d tau n or d tau l by dt having the role of beta. Fine. So these equations can be solved using a mean field approximation. I'm just not going into depth about how one can solve them. So the solution requires some mathematical treatment, and if we will solve them and convert it into continuum limit, we will be having a partial differential equation along with boundary conditions. Right? One can solve them comfortably and can find out that still we are having three phases: low density, high density, and maximal current. And the phase diagram seems to be like this. So this is a bit complex phase diagram. Very quickly I'll tell you. This is a controlling parameter alpha. This is parameter beta. Alpha beta, recall, left hand entry rate and right side entry rate. And we have a low density region here, high density region here, and maximal current here. Fine. So that means this information can be utilized to control the traffic on road. How? Because if the high density is there, that means I am having alpha beta value in this range, and if I want to get rid of, so I can increase either alpha or beta and can jump to this low density region so that I can avoid the traffic jam. So this simple modeling approach can actually help you in understanding the transport happening over the road network. So these models can be generalized, and later on we have generalized it for making it more realistic by incorporating many features which are present on road traffic, because the one which I have presented is the simplest one, and one can generalize it for the adaptability part. So one can also perform Monte Carlo simulation parallelly and can check whether your theory is working or not. So in this case, the Monte Carlo simulation validates the theoretical results. Fine. So these are the references which I have used to present the information. So the take-home message is we can understand the transportation process developed by nature and can actually understand them and develop the transportation systems for our own. Thank you. Thank you very much. If you have questions or queries, please feel free to ask.
Any questions? Thank you very much, sir, for arresting the lecture. Thank you, sir. The deep insight into the theoretical concepts and models of stochastic transport has enlightened us all about the notion. Thank you very much, sir. Now for the talk on the state of agriculture in India and possible technological interventions for evergreen revolution, we have among us Dr. Pushpinder Pal Singh, sir, Assistant Professor, Department of Physics, IIT Rupnagar. Dr. Singh is an experimental nuclear physicist with a passion for instrumentation. He earned a PhD in physics from Aligarh Muslim University for experimental investigations of low energy incomplete fusion carried out at the Inter-University Accelerator Center, New Delhi, for which he received the Professor C.V.K. Baba Best Thesis Award 2008 from the Indian Physics Association. After a postdoctoral stay at Tata Institute of Fundamental Research, Mumbai, and a national laboratory at Italy, he joined as a visiting scientist at Darmstadt, Germany. Later, in 2011, he joined the Department of Physics, IIT Ropar, where he is a project director and principal investigator of Agriculture and Water Technology Department Development Hub, established by Department of Science and Technology, Government of India. Dr. Singh is also the founder director of IIT Ropar Technology and Innovation Foundation. His research focuses on low energy nuclear reactions, rare decay studies, and deployment of cyber physical systems in the domain of environment,
agriculture, and water. I call upon Dr. Pushpinder Pal Singh, sir. Sir, please.
Thank you. Am I audible?
Yes, sir.
Okay, so I think you need to mute yourself. Yeah. So thank you very much for. I see. Okay, now it's better. Thank you very much for having me for this Punjab Science Congress, and probably a very nice introduction that you have given. I'm not sure if I will be living to the expectations and the introduction that you have given. My many colleagues have spoke today from IIT Ropar, and I know that one of my senior colleague, Professor Yasveer Singh, will be speaking after me. So I'm sandwiched in between, and I do not know if I will be able to live to the expectations. But the issue that I'm going to share with you, unlike the subject I work in, is quite an interesting issue. And it's important that we all understand the problem that is there in the agriculture domain. And we try to do whatever best we can do. As we all know, there has been a saying that knowing is not enough. We have to know how to apply the knowledge that we generate. So all what we are doing at IIT Ropar is we are trying to apply the knowledge that we have generated, and that too in the domain of agriculture and water. So now I will be presenting my slides. You have to guide me if everything is properly visible. In case things are not visible, please feel free to interrupt in between. Okay.
It's visible, sir.
Okay, thank you. So my title has already been narrated by you, that I will be talking about the state of agriculture in India and possible technological intervention for evergreen revolution. In this small talk, I will be going through where are we, that means the state of agriculture, and what are the issues that we have, although we know, because this is something very, very important for the living beings. And then I will be talking about the mega project that we are executing at IIT Ropar. So we know, allow me to take you to the history a bit. We know, or how we reached where we are today. We know that Green Revolution started in 1950. And the person who was responsible for Green Revolution worldwide is Norman Borlaug, is a German scientist. And he is known as the father of Green Revolution worldwide. He got the Nobel Peace Prize in 1970. But in India, Green Revolution entered in 1965. And it has started from the very state of Punjab. In India, the father of Green Revolution is Mr. M.S. Swaminathan. And he mentioned and coined a term called evergreen revolution in the very beginning of Green Revolution in our country. The very idea of the Green Revolution was that we will be going for environmentally sustainable agriculture, sustainable food security, and yet we will be preserving the biodiversity. So these were the three major pillars of the Green Revolution that India has started in 1965. Sustainable agriculture, sustainable food security, and the biodiversity. And that's how it was called Evergreen Revolution. And these terms were in the other Green Revolution, but not so beautifully highlighted. But what happened then? So after 1965, as we all know, that by 1970, Punjab alone started producing 70% of the country's total grain. in just 5 years of time. We started green revolution in 1965, and Punjab overtook it and started producing 70% of the total grain that country was producing in just 5 years of time. Now you see this success. Now this success has been seen by other states. And in the race, every state in the country aspire to achieve what Punjab got in just 5 years of time. And then how? They wanted to achieve the higher growth, the higher yield in the agriculture, or how we in Punjab started achieving the higher growth and higher agriculture. We started using a good amount of fertilizers and pesticides. And due to the excess and inappropriate application of fertilizers and pesticides, it was quite unfortunate that we had been told that this kind of fertilizers, if you use, this kind of pesticides, if you use, you will kill the insects which are damaging your agriculture or the produce. We have been told that if you use this kind of fertilizer, your growth will be better. But somehow, the knowledge of appropriate application has not been drained down to the people who were involved in the agriculture. And how things changed. We polluted the waterways. There has been of beneficial insects and wildlife. We contaminated the soil and water around us. And it became almost a practice to grow more than 3 crops, and in some time 4 crops on a farm in 1 year. And this has caused overuse of soil and water that has also rapidly depleted its nutrients. The irrigation practice has gone wrong. And in the entire exercise of growing more and more produce, we degraded the soil quality. The groundwater level has fallen down dramatically. As a result, we had content of hazardous substances in the soil and water. And because of this content of hazardous substances in the soil and water, we started getting numerous health issues because we contaminated everything that we eat, drink, or even breathe. Not only this, if I want to also remind you what Swaminathan said in one of his reports in the very beginning, that if agriculture goes wrong in the country, there is absolutely nothing else will have a chance to go right. And this is exactly what we did. We went wrong in the domain of agriculture in our country. And this is the typical scene that you see today. We have very, very bad quality water that is coming from the discharge of the industry, the discharge of cities. There are a lot of pollution, and the very same water is being consumed by the cattle, and the same cattle is giving us milk. The very same water is being consumed in many cases for the green produce. If you go to the metros like Kolkata, Delhi, Mumbai, the same water is used for growing vegetables and greens, and they are reaching to your kitchens. There has been also a lot of issues where the air has been contaminated by multiple reasons. Stubble burning is not such a big issue, but there are other issues which are disturbing the environment. Stubble burning comes just twice in a year, but there are many other issues which are killing the air quality. And we are eating and drinking everything that we are producing like this. So it's the typical scene. Now I want to give you few numbers, and I want to share with you what are the bigger issues. And the numbers are following. We know that the world population by 2050 will be 10 billion. And if we estimate that how much food, extra food do we need to feed 10 billion of population, it comes out to be 70% more food. 70% more food need to be produced in just 30 years of time from now. This is one issue. And I also want to share with you that what is the trend of our population. By 2030, we will be 143 crores. Now, 30% food, or more than 30% food that is produced globally is wasted. And the food that is wasted is equals to 25% of the fresh water. So there are two issues here. One, we need 70% more food to be produced, and out of which even presently we are wasting 30% of the food that is even produced today. And not only we are wasting the food that has 25% of the fresh water. We know that 65% of the people globally make their living through agriculture. And this number in India is beyond 80%. We also know that agriculture accounts for 4% of global GDP, which is higher, actually more than 20% for India. During the COVID time, when all the industry were collapsing and many countries were having a rapid downfall, India could survive, and it could survive because of agriculture. Because we have a very big share in our GDP that is coming from agriculture. We also know that agriculture accounts for 70% of fresh water use. So the two things that are coming out of this data is that we need more food to be produced by 2050. We have to do something for saving the food, the self-life improvement, so that the waste is minimized. And we have to take care of the fresh water. With this, I also want to share with you that the rural and urban population, this is probably connected with my first point where I am trying to impress upon you that we need 70% more food. But the amount of arable land, the agricultural land, is decreasing because we are increasing the urban settings everywhere. And by 2050, our urban population will cross the rural population. What does that essentially mean? It means that we will have less people living in the rural settings, and therefore the sector that will be damaged is agriculture. The migration of people from the rural areas. So then we have to do something for the agriculture, and we need something in the domain of technology intervention in this domain. Now, I also want to share with you that there is a huge gap in the demand and supply. You will be surprised to see these numbers that by 2030, India will suffer a shortfall of around 42 million tons of fruits and vegetables, unless we do something magical in the agriculture industry. So that is the situation typically. The situation typically is that by 2030, either we match the 42 million tons of fruits and vegetables by some mean, maybe we can save that 30% that we are wasting, and we grow more. This is the bigger issue. Forget about the global scenario. Even in the Indian scenario, we need 42 million tons of fruits and vegetables more by 2030. So how are we at IIT Roper? How are we doing a bit of our efforts in this direction? Of course, we alone cannot change the very landscape, but being a technological institute, our responsibility is being in the state of Punjab and connected with Haryana, Himachal, and Jammu Kashmir. Our responsibility is that we do something in the domain of agriculture and water so that by 2030, we could manage to contribute something in this direction. The other thing that I wanted to say here, which is also important, that the Green Revolution started from Punjab. Now, the solution of the problems in the domain of agriculture should also come in some way from Punjab. So that is how we at IIT Roper are pushing ourselves to make some solutions in the domain of agriculture. And I'm happy to share with you that Government of India in 2021 had awarded IIT Roper a Technology Innovation Hub in the framework of National Mission on Interdisciplinary Cyber Physical Systems. And the hub is named as ABAD, which is an acronym of Agriculture and Water Technology Development. Now, what is the vision of the hub? The vision of the hub is precisely what was the vision of Green Revolution. We would like to contribute for environmentally sustainable and profitable agriculture. We wish to contribute for quality food, yet we want to preserve in the best possible manner the biodiversity. Now, why the preservation of biodiversity is important? The preservation of biodiversity is important, and why this is connected with agriculture. We have been taught in the beginning, when we were kids, that there are a lot of beneficial insects in the fields. We are working on the technology interventions where you can identify what are the beneficial insects, and when they are increasing their numbers, and at that time, at that duration, you don't use pesticides in the agriculture. So this knowledge we want to give to our farmers, that what is that time when you should not apply pesticides at all in your fields, so that you can save the insects or the biodiversity, which is beneficial for the agriculture. And that's how we can move towards what we call Green Revolution. Now, what is our focus? Our focus is that we will be developing cyber physical systems, hardware solutions for the domain of agriculture. And we wish to be a place to go for cyber physical systems in agri-tech by 2024 in our country, which will be supporting extensively what we call Skill India, Make in India, Digital India, and Atmanirbhar Bharat. With this, I would also like to flesh and share with you that there has been huge expectations. IIT Roper has been granted 110 crore rupees for this kind of technological intervention for agriculture. And you will be happy to see that the day the education minister has announced this, he said the innovation hub approved by Government of India at IIT Roper will help the agriculture and water sector in the country by bringing solutions for stubble management, water quality improvement, mapping of hazardous substances in water, and soil and their treatment. And he hashtagged it the New India. Now, why I'm showing you this particular tweet? I'm showing you this particular tweet that there has been a hope. He said New India. And the tweet was liked by the higher officials of the country, our Prime Minister Narendra Modi also that time. So this puts a huge pressure on us that we should do something better. So now what is, very quickly I would like to share with you, what is this national mission on interdisciplinary cyber physical systems, so that you can connect the solutions that we are talking about. Today, as you know, information flows much faster than it was flowing a decade ago. We have seen during the COVID time, there is an object called Arogya Setu. Arogya Setu uses your mobile phone and gives you information about if there are people who are contaminated with COVID. We have seen Google Classrooms. They have helped us for teaching and learning. Even I'm able to communicate to you today. I'm able to communicate to you today because of the Google Classrooms or the Google Meet. So the information flow is very, very fast. There are technological intervention even on the road, like FASTag. Earlier, you have to take a parchi, you have to give money, and then you go and cross the toll. Today, you don't have to do it. In the developing countries, people and things are even much more connected. And therefore, as per the prediction that we understand, by 2030, each and everything around us will be connected with what we call electronic systems, which are capable of making intelligent decisions efficiently. And these electronic systems are called cyber physical systems. Now, I have been talking about cyber physical systems in a recent conference, and somebody asked me, what do you mean by cyber physical system? So I thought of having this table here just for your information in case some of you have the very same question. You know that in 1926, we have started something called teleautomation. Nikola Tesla coined this term called teleautomation. Now, this teleautomation term has graduated towards 2006 and termed as cyber physical system by none other than someone called Helen Gill. She is the program director of embedded systems at National Science Foundation in the United States. So the cyber physical system is nothing but the advanced version of teleautomation. So you are automating the systems. For example, if you want to switch on your air conditioner at home, you can do it from the airport these days. So that by the time you reach home, your house is cool enough to accommodate you. So the government of India has launched a national mission in this direction to match the global rapid rise of intelligent systems. There will be a lot of R&D happening for the training, skilling in the robotics, AI-based big data analysis, which is very important, and extensive use of Internet of Things or Internet of Nano Things, and to develop and deploy these technologies in the domain of agriculture and water, health and environment, manufacturing, infrastructure, geoinformation systems, etc. And I'm happy to share with you that we have been one of the 7 institutes which have been identified to host a technology innovation hub. Now, what will be the operating content for us? The operating content for us, as you understand, that nearly all Indian villages will be connected with the paved road by 2030. So we'll have road in almost all Indian villages. All of India will have a reliable electricity supply by 2030, we hope so. And internet will be cheap and universal. There are chances that we will have 6G by 2030. Today we have 5G. AI will be near human intelligence, so there will be a lot of artificial intelligence systems coming to the domain. A majority of enterprise data globally will be stored on the cloud. So the cloud services will also be very much available by 2030. Now, what does that mean? So how all of it that I'm showing here is going to affect and help the agriculture domain in terms of automation. If you look at the smartphone and internet users by 2019, this is the number. 90% people will be going to have mobile phones by 2030. And 77% people were already in 2019 had the internet. So this is going to change the very landscape. So can we use the data, internet, artificial intelligence, the mobile phone for providing you the right kind of information? So with this, we are developing technology in the new farming systems, which includes indoor and vertical farming. We are working on digital farming. We are working on midstream technologies, which include food safety and traceability technologies, etc. We are working on agri-business marketplaces. We are working on bioenergy and biomaterials. And the entire technology innovation hub is divided into 5 verticals and 1 horizontal, in which we are working on stubble management. We are working on precision agriculture and automation. We are working on naturally occurring and artificially infused radioisotopes in the soil and water. We are trying to trace them so we can correlate and understand, is there any connection with the arsenic and cancer in the country? We are working on water treatment and management, water treatment even for agriculture. And this will impact biotechnology, will produce tastier and more nutrient food and eco-friendly crops and food. Farmers will be connected and digitized and autonomous. There will be more fresh greens. There will be more diversified situation of food sources. Food will increasingly and scientifically replace the medicine. We believe that preventive health care can be taken care just by the food. But we have been calling it Ayurveda, we can call it food. Majority of the rural jobs, as we understood, that by in few years of time, our rural population will decrease. But there will be non-agro jobs in the rural area because of the rapid rise of the cyber physical systems in the country. I want to also share with you that the Agriculture and Water Technology Development Hub at IIT Ropar has trained more than 450 personnel so far. We have supported 5 startups. 6 products have been developed so far. More than 60 people are working regularly. We are offering cyber physical system outreach courses, etc. I want to also share with you that there are products that have been developed for the first time in the country and very well received by the Government of India and Digital India. We are working on many other products like Ambitag, Extract, Indus and Bias are the 2 nanobubble water quality improvement generators. We are working on Farm 1, which is an interesting. The other thing that I wanted to share with you is the fishery market. The fishery market in the country is going to be 2,250 billion rupees by just 2026. But we are not ready for it. Ready for it in the sense that we are not making aerators. We are not making the fish deboning machines. You cannot consume the entire fish that you produce. Therefore, you have to have the preservation techniques. And to have the preservation techniques, you have to develop your own aerators and own fish deboning machines. And these 2 things we have taken up as a challenge at IIT Ropar and we are developing. I also want to share with you, because my talk is now going to be end, and I hurried up a little bit considering the time. We are running something called Internship Carnival, and this Internship Carnival is open for everybody. So those who are hearing today, they can motivate students to join. The 2022 Internship Carnival will be announced on 28th of Feb. And in this carnival, what we do is we select 100 interns every year. And these 100 interns will be working on 10 problems. There will be teams. And successful online internship carnival that we have created, I want to share with you that 14 patents have been filed out of that carnival. So means a student did the work and they got the patent. 18 are under review, 11 design registrations are being filed, and this have been very well appreciated by the government. We are doing other 2 courses, which is artificial intelligence and cyber physical systems for agriculture automation. And the course is practically free for anybody from any institute. And we are also not putting the restrictions like you should be BTech in final year. You can be in BTech first year, or you can be a science graduate. You can be anybody with the knowledge of programming. And in this, we are giving the hardware, and we are only charging the hardware cost. So with this, I would like to close for today, and I would like to hear from you if you have questions quickly. And with this, I thank you for listening. And if there are questions, I will be happy to respond to you, or queries. I will be happy to respond to your queries.
Thank you so much, sir.
Good morning, sir.
Any questions from the audience?
Ma'am, may I ask?
Yeah, please go ahead.
Good morning, sir.
Good morning.
So you have said a term, digital farming. Could you please explain it?
Yeah. So, see, I was explaining the cyber physical systems to you. So, when we talk about digital farming, that means that you are trying to automate your farming systems. For example, today, I give you a very quick example and probably apt. Today, we are talking about autonomous vehicles. A country like India cannot dream of autonomous vehicles today and not even next 30 years. Why? Because our road conditions are such, our driving aptitude is such that we cannot consider, or we probably will not have, at least in next 30 years, the autonomous vehicles on the road. But what we can do for the agriculture, if you make your tractors autonomous, you can avoid being in the field all the time. If you have a 10-acre of field and your tractor are autonomous, you can control it from wherever you are. You can just put it in the field. So the future of agri-automation or in the automation vehicles is the agriculture. In India, if we can think of automation, we can think in agriculture. Because in the field, there is nobody. Your tractor is just sowing whatever doing. So it is possible. Now, this is just one thing that I wanted to give you an example. There are many other ways to look at it in the automation, or so this is called digital. Now, the other thing that I quickly can give you an example is that when you go to the fields, how do you apply the fertilizers? You apply fertilizers because somebody told you that you apply fertilizer 3 times. This time, this time, this time. Or what you do is you get the education from your neighbor. If their field is looking greener and your field is looking slightly yellowish, what you will do? You will put nitrogenous fertilizer, so your field also get greener. But the question here is whether your field need the nitrogenous fertilizer or not, and what is the amount that your field need nitrogenous fertilizer. Then there is a device called green seeker. We are developing a green seeker, and this device we will be able to give to the farmers. It will be like a clip. So you clip on the plant. This device will guide you that the nitrogen content in the plant is this much, and therefore this should be the quantum of nitrogenous fertilizer that you should spray or apply in your. It should not be driven by the person who is selling the fertilizer to you. It should be driven by the field. So this is where what we call digital agriculture comes. The same thing happens with the water. You know that today we go and do flood irrigation. It has been discussed, it has been told that for many rice varieties, you do not need flooding. And for any rice variety, you do not need flooding. You need to have the right kind of humidity maintained in the field, and rice is good with that. So can we have a system which can guide you about how much water you need to put in? So this kind of systems we are developing. And for example, if you can quickly understand the NPK value of your soil, you can decide on how much fertilizer you should apply during the seed sowing. So this kind of systems we are developing, which are cost effective, and yet they are efficient and working fine. So these all things comes under what we call digital agriculture. If I'm not clear, please let me know.
Thank you very much, sir, for your explanation. Sir, I have a next question regarding this. So biotic seeds are not accepted by a number of people because they have an assumption that they are using animal genes. So what's your take on this, sir? Matlab, how will you explain and try to educate them properly about these biotic seeds or biotic farming?
See, I tell you something. What happens is that perceptions are only possible to be killed by the right kind of positivity in the society. And we all, there has been a time when the jeans as a cloth was considered the cloth of poor, the cloth of laborer class, because jeans as a cloth is very rugged and tough. Today, all of us go and buy levies in sometimes 6,000 rupees. And we are not caring about that people will think that this is a cloth of labor class. This has happened because India, in particular, the consumer market goes top to bottom, go from bottom to. So we have to target the top consumers. And when it become a practice in the so-called higher society, the people at the lower level, they start following. People like us, people like me, they will start following that, oh, everybody is eating this, no problem. Now, the other thing that I want to tell you, that there is something called black soldier fly. I want to give you an extreme example of this. There is something called black soldier fly, and black soldier fly is an insect that gives something like 600 eggs in the lifetime, a duration of 20 days. And these eggs can be harvested. You can extract very, very high quality protein from these eggs. You can extract high quality polymer. You can extract some kind of oil, which is very similar in characteristics as that of coconut oil. Now, you will ask me that what I will do with all these items, all these objects, because you are extracting something from larvas. Eggs are then transforming into larvae, and then you are asking me to eat larvae of the insect. Now tell me, what is the difference between the egg that we are eating? They are also very rich in protein. We are eating eggs, the eggs from the birds like hen. And the same thing is this. Now, if you go to the European markets today or Chinese markets today, you have black soldier flies, larvae already in the bread in the supermarket. People are buying it. So there is absolutely no return back of this. You will see in the due course of time. However, it will take time. You will, if you analyze, if you are one of those person who is analyzing the food pattern of the Indians, even, you can ask people. If you have grandmother already or your mother, you talk to them. How common paneer was in our life. How common eggs were in our life some 30 years back or 35 years back. And how common it is today. We all are eating paneer every day. We all are eating eggs every day. So that this particular thing that you ask me, this will also come up. But it will take time. It won't change in one day.
Thank you so much, sir.
My pleasure.
Thank you so much, sir. Thank you so much, sir, for enlightening your enlightening talk. You have addressed burning topics of the society, that is sustainable agriculture and sustainable food security, water quality improvement, which are key factors towards sustainable future. Thank you so much, sir, for your wonderful talk. Thank you so much, sir.
My pleasure.
Moving forward, we have among us Dr. Jashveer Singh Ji. Dr. Yashveer Singh Ji is an associate professor at Department of Chemistry, IIT Ropar. Also serves as an associate faculty at the Department of Biomedical Engineering at the Institute. He received his PhD degree at the University of Allahabad and did postdoctoral research at Indian Institute of Science, Bangalore, Joseph Fourier University, France, Reuters University, USA. His research interests are in the broad areas of polymeric biomaterials, drug delivery, and tissue engineering. In particular, his group is working on polymer and peptide-based hydrogels for microbicide delivery, chemotherapeutic agents delivery, bound healing, and tissue engineering applications. He is an assistant editor of 6th edition of Martin's Physical Pharmacy and Pharmaceutical Sciences, a major textbook for pharmacy school worldwide. Without any delay, I would like to invite Dr. Yashveer Singh ji for his talk entitled as Chemistry for Sustainable Development. Sir, over to you. Sir, Yashveer sir.
Yes, am I audible?
Yes, sir.
Okay, so I will, very wonderful talk, Pushpendra, that you gave today. Wonderful it was. I enjoyed your talk. And thanks for the invitation to the organizers, for giving me invitation to attend this science congress. What I am going to do is, because time is short, so I will just talk about few of the things that are, I will talk about sustainable development, then I will talk about two, 3, in terms of chemistry, restricted to chemistry, 2, 3 things that can be tried or are being tried, but what are the challenges that are there. And then if time permits, I will present 2, 3 slides on my research, because research will take an hour. My research will take an hour at least to present. So I have just a glimpse of one particular research, but that I will present in the end. So I am now, can you see the slide?
Yes, sir.
Okay, so I'm going to talk about chemistry for sustainable development. And what is sustainable living? First we talk about, and then we talk about, how this chemistry, the way we do, what is the challenge? And then, of course, we think about some of the ways that we can use to address this issue. So, we use natural resources that are present on Earth, and that supports our life, not our life, basically all life forms. And of course, the economic activity that is required to, sustain this, living process here. So that is there, but we are using it too much. So basically, there has to be a control on that. And this sustainable development or living is a philosophy or practice which basically means that you don't do harm when you are taking resources from Earth. You must have minimal impact on harmful impact of your activity or your actions on society and the environment. That is basically what is sustainable development, and it can be looked in different ways. So we will just talk about how we can actually practice sustainable development or living. So basically it is as we call it net zero living or zero energy balance living. Of course, in theory, it is very easy, but in practice, it is difficult, because what it entails is this, that you have to return whatever you take to Earth, or your sources of that resources must be, replenishable, renewable. That is one aspect. And then the second aspect is, of course, when you are taking resources from Earth, it must cause minimal harm while you are taking this resources. Of course, this situation is not possible, all the possible, but that's where you try to take your operations. That's the direction that you have to go through. And sustainability has different aspects. You need to have a sustainable economics, you need to have a sustainable society, but environment is most important, because of course everything actually depends on environment. All the resources come from environment. So environmental sustainability is of course of prime importance. You can look at this, one more way of, looking at sustainable living is this, that, that as a society, you are withdrawing resources from the Earth. But while doing so, you are not, touching the fault lines that actually cause some harm. For example, you are doing farming. There is no harm in farming, but the farming must be done in a way that the soil is replenished. Or the use of pesticide that has no, that there are so many harmful impact, that must not be done. So that is basically what is that you keep drawing your resources that you need to carry out your life and economic activity, but not without touching the fault lines that might lead to problems like, there is a climate change, there is a biodiversity loss, there is a land conversion, all that, the problem that so you should not overshoot that is what is the whole thing. But the more important part of this sustainable living, of course, is that you must also leave resources for the future generation. See, we can use it responsibly, that is only one part of it. Our future generation, our kids, should also have their share in the resources when they become, young and adult. But are we doing it? So, if you look at the way we are consuming our resources, so, they actually started observing what is called Earth Overshoot Day. So that's the day when humanity has used up all the resources that they should have used in that year. And you see how the situation was. If you look at this graph, and if you look at in the 70s, you will notice that the overshoot day was coming in, in December, which is that we were almost carrying out through the year by the using the resources that were supposed to be used in that year, which is very fine. But by 2018, this overshoot day is, coming in August. What does it mean? That we are consuming resources by the time our year is half over. And if you do some calculation, basically we need 1.7 Earths to meet our resources need. That is not possible. That is not possible. And actually, I have presented here average. If I look at a US lifestyle, then we will perhaps need 5 Earths. That is, of course, not possible. That is, of course, not possible. Now, this is basically, what will be the consequences of, unsustainable living? There are many, but few important ones are summarized here. You can read it. It's a general knowledge type. There is not much science, but, quality of environment is something that will deteriorate. There will be more landfills around, you in cities and villages. Many animal and plants will go extinct. There will be number of new diseases that will come. Climate change will be harsher. Sea levels will rise. Life will be very, very harsh for lower income communities. There will be decline in the soil quality. There will be fewer green spaces. And of course, more importantly, there will not be enough natural resources to meet the need of future generations. So this is basically consequences. So then how do you do sustainable living? Basically, 3 major things that are important in sustainable living or development is that you reduce the use of resources as much as possible, reuse as much as possible, recycle as much as possible. Of course, all this sounds very good, but you will ask that, how to use it in practice. So basically use renewable energy, like, sun, wind, water, geothermal, biomass, use organic or regenerative farming. Use plant-rich diet, instead of depending on meat. Grow your own food. By your own food, at least what I meant here is that the local communities must be sufficient to meet their need. There is no need to import vegetables from around the country or now across the globe. There is no need. So you must grow your own food. Reduce the food waste. Use public transport where possible, and develop sustainable buildings, and achieve self-sufficiency. So basically, if I summarize, there are 4 aspects of sustainable development or living. Social sustainability, that actually focuses on maintaining and improving the social quality. Human, basically we invest in health and education system and services. Economic activity. to improve the social equality, and of course, environmental sustainability, which is very, very important because that natural capital that you use, resources that you use come from environment. So there are, different components of sustainable development. And now, actually, based on that, actually, United Nations Development Program has actually adopted 17 what is called United Nations Sustainable Development Goals. And you see, if you read them, of course, there is a clean water, there is a, organic and regenerative farming, all that is there, reduce pollution, all that is there. But it also talk about, zero hunger, no poverty, good health, gender equality, because, a sustainable development entails everything. You must have freedom, you must have, freedom to get resources, you must have all those things. So this is basically UN Sustainable Development Goals, and that is what we should adhere to. All communities are expected to adhere to. So what is the principle of this UN Sustainable Development Goals? Basically that no one should be left behind, and there should be a holistic approach towards development, and there should be something left, for the future generation. So, with this I am done. Now I am going to talk about, why chemistry is a challenging, thing when we look at sustainable development. So if you look, at any reaction, let's say that, you have a chemical reaction in your mind. There are two reactions, A and B, that actually react to form a product. In this process, there will be solvent, there will be reagents and all that. The problem is this, that in this reaction, you will be using a lot of material. And then to drive the reaction towards completion, you will use the reagents, the other starting materials, etc., in excess. And then you get the product. It is written that you are getting the product, but what is hidden here, that you never get 100% product. You get partial product. So what is happening here, that the starting material that you are using in the reaction is not all consumed. A part is left. That will, of course, contribute to waste, toxic waste. Then you are using solvents and reagents. Now, don't look at the labs that you have in your college. For example, there, you generate small amount of waste. But think about company. You will be using millions of liters of solvents, in country, billions of tons of waste will be generated. So we are talking in that term. Then because this product is not completely formed, there has to be purification. Again, you have impurities that actually contribute to the waste. So if you look at this chemistry process, it is truly non-sustainable. The resources that we use are many times non-renewable. So if we keep using them at that pace, there will be no resources left for future generation. There is incomplete conversion of starting material, and that is generating waste. There is use of harmful solvents and reagents in excess that actually also generates waste. Purified products are purified, and again the process generates waste. So, all this has very deleterious consequences to the environment and our sustainable development goal. And to address that, actually, I am just going to talk 2-3 slides on green chemistry and then go to other things. So, basically this green chemistry concept was developed, and basically what it says, that it developed your products and processes, chemical processes, in a way that it either reduces or eliminates the use and generation of hazardous substances. And what does green chemistry seek to? Reduce our waste, particularly if the waste is toxic. Reduce the consumption of resources, or encourage the employment of renewable resources. And reduce, all industrial units actually work on a lot of energy demand. So reduce energy consumption as much as possible. So the same scientists actually, Paul Anastas and John Warner, actually also gave us actually 12 principles on which actually this green chemistry should work around. And that was, first is that it is always better to prevent waste rather than generating it and then treating it. Treating itself will require a lot of chemicals. Synthetic methodologies must be designed in such a way that most of the starting material is incorporated into it, so that there is no reactant waste. And synthetic methodologies should be designed in such a way that they do not generate toxic waste. Product should be designed in such a way that it preserves its activity, but toxicity. And use of auxiliary substances like solvent for purification, separation reagents, those solvents, those should be made unnecessary, because they actually contribute to unsustainable situation that cannot be addressed. And of course, energy requirement should always be monitored and it should be minimized. I will give you one example also, and you will see how these things can be done. Your feedstock, from where the raw material you are coming, it must be renewable. Your synthetic process must not include, this derivatization where you protect a group and then deprotect a group. All that looks like a fancy chemistry, but actually it adds millions of liters of, solvents, reagents, and other toxic waste. And it is always better to use catalyst rather than using stoichiometric reagents, because stoichiometric reagents must be present in large quantity. Many times you are chemistry students, so you might know, your chemistry faculty, you might be knowing that stoichiometric reagents are added in excess to drive the reaction towards the end. And products should not, persist in the environment after the end of their functions. For example, polythene is an example of non-sustainable product. It stays in the environment. There must be analytical methodologies that must monitor, if there is any generation of, toxic waste, and how to, address or control it. And more importantly, your reaction should be designed in such a way that there is less chance of chemical accidents. So this is basically green chemistry principle. And I am going to talk about that, how you can think about these things and actually work around it. And this is one very good example of ibuprofen. Ibuprofen is a drug and it is used around the world to treat pain, fever, and signs of inflammation. Its commercial synthesis was actually developed by, Boots company, which is in United States, and this same synthesis was used around the world with some difference here and there. Now, if you look at this chemistry, so you notice that they were doing 6 steps of synthesis. 6 steps of synthesis to get this compound. Now, forget these solvents and reagents and other things that they are adding. We just try to look at that what is the percentage atom economy. That means how much of starting material is being converted to product. So if you look at this starting material here and here, and you calculate their molar mass, and you also calculate the molar mass of this, atoms that are present in the product. So this molar mass here is 206, and this molar mass here is basically 514.5. So if you put this value and then multiply by 100, you get 40%. Think about it, that ibuprofen is synthesized around the world commercially using this method, and the percentage atom economy is only 40%. Only 40% of the atoms in starting material are going into the product. Rest 60% is only contributing to waste. Very, very wasteful procedure. And so this company worked on this and actually see how things can be done. They actually were able to come up with this a very simple process. So if you look at this process, they are doing the synthesis of ibuprofen, which is a drug, only in 3 steps. So you are an organic chemist, and you know that if I reduce the number of steps from 6 to 3, green chemistry is already done, because there is less use of solvents, there is less use of, reagents, etc., and, impurities, all that. But you look at this, actually, there are 2, 3, 4 things that are actually very greenish or green chemistry type. One is this, that they are using this HF and, Raney nickel and catalytic amount. So because they are using catalyst in all the 3 processes, so they are being used in a little amount. Catalysts are always used in very little amount. So they do not contribute to the molar mass of starting material. So that is one advantage. The second advantage is this, that this is the starting material. And if I calculate the atoms that are going here and the atoms that are going here, it is basically 2006 divided by 266 into 100. And you get 77%. So your now percentage, atom economy is 77%. So 77% of the starting material is going into the product compared to 40%. Just we have almost doubled it. But then that was not all. They also found that they are using this, acetic anhydride. This acetic anhydride in the process is converted to acetic acid that can be isolated and separated and used by the industry. So, this waste is not waste. It is now a, material, raw material for industrial process. So it can be used there. So if you put that also in account, they have made this, percentage atom economy 99%. And of course, they also did not use auxiliary materials. So that also contributes to this green process. And in fact, this process was actually chosen for the green chemistry medal, and this company received that award, green chemistry award. So this is basically, many times that, question that you hear, the problem that why green chemistry is not adopted everywhere, because you have to start thinking. Sometimes, people who are working in this, they say that, how we do, it's very difficult, or ek step se green ho jayega, but how it will affect others. See, even if you take care of one industrial process and make it green, that is also going to contribute bit by bit, actually, makes it a bigger contribution. So it should not be said that, no, why should I bother about one step? Others are also doing. No, you think about your process, and bit by bit, actually, you will reach the goal that we are talking about. Another thing that is also very interesting is, because in green chemistry, so it is kind of related. See, in green chemistry principles, I talk about that it is always better to use, catalyst instead of stoichiometric reagents. Now, so when we talk about catalyst, we should also talk about enzymes. Now, why enzymes are, first thing, what are enzymes? Enzymes are basically three-dimensional proteins, polypeptides, which are folded into a three-dimensional structure. Sometimes they have also quaternary structure. And usually this is a big protein, but they carry cavities or active site. And the catalytic action that is carried by this enzyme is because of this active site, where amino acid side chain is present. It actually, accommodates the substrate, and then the substrate interacts with the side chains that are present in the active sites here, and then actually catalysis is done. So enzymes are called biocatalysts, but they are present in cell. You can use the cell itself, or you can isolate the enzyme to carry out this catalysis in industrial processes. It is possible to use it, in commercial processes. And what is the advantage of this enzyme? That, it reduces the activation energy of this chemical transformation, and that's why it happens faster. But that any catalyst can do. I am going to talk about that. What is the advantage of, having an enzyme in industrial process? So there are many. One thing is this, that these enzymes are selective for one substrate. So, they are very, very selective for one substrate. That is one advantage. Second advantage is this, that chemical transformation in cells are done in water. And same thing, aqueous media can be used, to carry out these enzyme-based catalysis. So, using water is very, very green. Then, if, there is a stereochemistry involved, of course, you get optically pure isomers. You don't get racemic mixtures when enzyme catalyzes reaction in cells. And of course, there is no product purification. So basically, reactions can be done in ambient condition. That means body temperature and, the atmospheric pressure. It can be done in aqueous media. It is specific. So all these advantages make it very, very green. And therefore, there is increasing focus on enzymes because they are green, and also because it is now a chemistry that everyone understand that if there are two enantiomers, your drug is, you prepare a drug as a racemic mixture. Many times it is one enantiomer, that is actually active, not the other. And in chemical processes, you have to actually, do a lot to do either an enantiomer selective synthesis or to purify them. So that add to the non-sustainable process. And how we can address that through enzymes, I will give you one example. So are enzymes, used in industrial process? Of course, they are used. And there is a whole, laundry list of this enzyme that are already used in enzymes, already used in industrial process. There is one more slide. But the question that one can ask, that if enzymes are such a beautiful molecules, why we are not seeing them all around or in all the industrial processes? Because there are some problems. Enzyme is a protein. Protein has a tertiary structure, quaternary structure. So if enzyme is exposed to a harsh condition in terms of pH or temperature, there is a likelihood that it may go denaturation, loss of higher structure, and therefore action. And because it is specific or selective towards a substrate, obviously that is not very desirable in the industrial setting, because you want the same enzyme to be used for different purposes. Used for different purposes. So how can you address that? The challenge I will talk about. But before that, let's talk about one particular example, that how enzymes are desirable. So if you look at this process, we are talking about a drug, pregabalin, which is an anticonvulsant. It is used to treat seizure, neuropathic pain, and this sleep and mood disorders. So that is the condition that is used. Now, when you prepare this drug, by chemical processes, what you get is a racemic mixture. But in this racemic mixture, the activity, the drug, the part that is active is actually S enantiomer, not the R. So, your chemistry synthesis process, of course, always leads to racemic mixture. So obviously that is not a very desirable situation. So what happened, that they started using, bisphosphine, rhodium, and nitrulase to carry out asymmetric synthesis of this S enantiomer of this compound, which is used as a drug. But they found that the process is not very cost effective, and it has environmental concerns. So what they started doing using enzyme. And this process is so simple that they actually do not extract even the enzymes. Actually, this cell culture itself is taken. So, Arthrobacter species, can be used, and the esterases enzyme that is present in this bacteria actually converts this racemic product into, this two separate, enantiomers, and this S isomer, which is biologically active, is actually in 95% enantiomeric excess. So this is, the point that I wanted to make, that, that when you are trying to deal with a drug which is chiral, you cannot use traditional chemistry processes, because that will actually add a whole lot of reagent and solvents and purification challenges. But if you can use enzyme, obviously there is a benefit, because you can actually synthesize those, initial selective, asymmetric synthesis can be carried out using enzymes. So that is basically the benefit of using enzymes. But there is, this problem that I talked about, and so the problem is this, that that enzymes are selective for a substrate, which sounds good. But when we talk about industrial processes, obviously industry will be interested in using enzymes which can be applied to processes across the board. Many more processes, not one enzyme for one process, or similar processes. So they would like to extend the scope, and also they would like to deal with the risk of denaturation or loss of biological activity that actually enzymes suffer from. So do remember, as I said when I was in this slide, that enzymes are proteins and they have a big structure, but the part that is carrying out this catalytic activity is small. The active site is small, not that big. And basically, you can, make small molecules or, nano assemblies that actually mimic this active site to carry out this, catalysis process that is catalyzed by this particular enzyme. And this is basically called enzyme mimic. Enzyme mimic is basically a growing field of research, and what actually scientists are trying to do, they are looking at their enzyme and they are creating systems that can mimic that smaller system. Of course, you can use dendrimer, you can use you can use nanoparticles, you can use anything that you want, you can use organic molecules, but there are peptides also which are interesting. Why peptides are interesting? Because proteins are polypeptides, folded, three-dimensionally folded polypeptides. So the part, basically, the part that is active site is basically a peptide sequence, So when we use peptide to mimic an enzyme, it is more natural mimic. And that's why there is an interest in using this peptide-based enzyme mimics. So here you see in this case what they did, they took histidine-rich peptides, they took guanine-rich DNA, they took hemine, porphyrin groups which contains iron and chloride ions. So actually, what they did, they actually assembled them into a nanostructure, and what they found that this actually works like a peroxidase enzyme. What does a peroxidase enzyme does? It actually converts hydrogen peroxide to water. Hydrogen peroxide is toxic for cells. That is one major function of this, peroxidase enzyme. Now, peroxidase enzyme is a very big enzyme, but the same thing can be done by, having this histidine-rich peptides with heme. So this is the catalytic site, which is complex with peptides and this guanine-rich DNA to form this nano assembly, and then this nano assembly actually carries out the catalytic activity. This is, of course, a very, very intensely growing field of research, enzyme mimics. But of course, it is still at research. Not much has been done if you think about, in terms of commercial importance. I wanted to talk about my research, but at this point of time, I am skipping it because I want to talk about, this very interesting thing, synthetic biology in 2 minutes. So synthetic biology, basically, if you try to define, there could be, different way of describing it. But what I am trying to do here is basically, I am going to talk about, basically, when we talk about synthetic biology, I am talking about an organism created in the lab that did not exist, in the natural world before. So in that sense, I am going to talk about. And how these things started, looking possible. So there, there is this institute, Craig Venter Institute in USA, and what they thought that, if we use the word gene, which means individual gene, and when we talk genome, genome means entire genes of an organism. So what these scientists actually said, that can we transplant, remember that, complete genome, entire genome of one organism to other? That's the question that they asked. And what they did, they actually took 2 bacteria. One is this and second is this. And they were able to transfer the genome of this organism to this organism. And this organism, after receiving the genome, actually started behaving like this organism. So like this organism. So you see, this organism is not behaving like it used to behave. So if you look this organism, after this transplant, they found that it is phenotypically similar to this, not this. So that research actually showed that it is possible to, transfer the genome of one organism to other. Then this actually is same thing. I am trying to describe the synthetic biology. So I have already discussed this, and I will just go to the other experiment they did. And so what they did, they then ask another question, that can we synthesize a genome? See, now I am talking about chemical synthesis in lab. So there are in laboratories nowadays automated DNA synthesizer. So if you have that, you can actually chemically synthesize genome. And what they did, they carried out this genome of this, this bacteria, and then transferred it to this. After this organism received the genome from this organism, actually, the native gene of this organism were destroyed by the protein synthesized by this synthetic genome. So basically what is happening here, that these scientists have chemically synthesized a genome that is being transferred to another organism where it destroys the native genes that were already there. And
Excuse me, sir.
Yes. Yes.
Sir, actually, because of the time-bounded schedule of the next session to be started, can we please a bit
Okay,
make
so
it
I will
maybe?
complete it. So I will skip this, and basically I will conclude. So so basically as I presented, that chemical processes used in the industry are often harmful to living organisms and the environment. And that part I have actually explained, that how they are so harmful, to living organisms and also to the environment. And also, if you keep doing chemistry the way it is being done, it is in contravention to sustainable development goals, which actually seeks a better future for all. In this way, there will be so much pollution, there will be so much waste, there will be no resources left for a future. So this actually, the challenges that are coming in this traditional chemistry processes can be actually addressed by using green chemistry, enzyme technology, and actually synthetic microorganism. I could not discuss this third interesting part, but you can look at it by searching appropriate literature on synthetic biology. And then overall, these process immense potential so far as sustainable development goals are concerned, but more work is needed so that they can be adopted to a wide range of situations. They are showing promise, they are being used in restricted way, but more needs to be done so that you see them apply to much wider scale. And then I would like to conclude with this is my group. This is my group here at IIT Ropar. I have groups at chemistry and biomedical engineering. So this is the combined group. These are my students. These 3 students have already graduated. I have active collaboration with these Dr. Raj Kishore, Rajesh Nair, and Drupal. They are at IIT Ropar, and he is at CSIR in Jammu. I have also received funding. Our group has also received funding from CSIR, SERV, and now we have a DBT grant. So I actually acknowledge the financial assistance from them. Thank you for your attention, kind attention.
Thank you very much, sir, for this informative lecture. The deep insight that you have provided on the topic of green chemistry and enzyme technology, which are the need of the hour to head towards development of science and technology for sustainable future, is a very informative thing. Thank you very much, sir, for being with us. Our next speaker, Dr. R.C. Sopti, as mentioned in our schedule, due to some urgency, will not be able to join during the session. I'm sure his absence is going to be felt greatly. At the same time, we are very grateful to Dr. Adarsh Palvich for accepting our request at the last minute. We are indebted to you for being with us, sir. Dr. Adarsh Palvich, presently Chairman of Punjab Pollution Control Board, is a renowned environmentalist, able administrator cum organizer, professor, and former head Department of Botanical and Environmental Sciences, Guru Nanak Dev University, Amritsar, and President Vigyan Parishad Panchayat. Dr. Vij is having teaching and research experience of more than 27 years,
about 118 publications in national and international journals, and have supervised 13 PhD scholars. He has been awarded Distinguished Teacher Award 2012 and Environmentalist of the Year 2016 and 2018. He also worked as director of UGC Human Resource Development Center and project coordinator RUSA, Government of India at Guru Nanak Dev University. Dr. Witt is the only professional member of state-level Environment Impact Assessment Authority, Punjab, nominated by Ministry of Environment, Forests and Climate Change, Government of India, for granting environment clearance of the major developmental projects in the state. His consistent work in the field has led to his nomination for the Deshbhakt Sardar Lal Singh Oration Award. I now call upon Dr. Adarsh Pal Vij to present his Deshbhakt Singh Lal Singh Oration lecture, sir.
Hello, good morning, one and all. I'm audible?
Yes, sir.
Thank you. I think you can stop this screen sharing, so it will be. So good morning and namaste, sabnu pyar bhari sat sri akal. Thank you very much for giving me this opportunity to the organizer, to the Deshbhakt University for this particular lecture, and that too in a very renowned association, Punjab Science Congress Association, which is one of the leading organization of the state, and in the galaxy of the scientists. In the morning, I think there were wonderful lectures related to the various aspects of the science, rather modern science. I think you have been over-exhausted with the so many new ideas, new researchers. And thanks to the colleagues joined here, scientists, and Dr. Bhatt, who is chairing this particular session, my colleague, my friend at Punjab State Council for Science and Technology. So this Punjab Science Congress has developed an association at Punjab level, and every year these type of conferences where the whole science has been taken care is very important. So today, not taking much time because it is already late and you have been exhausted by listening those lectures. So I thought I should talk of the general science. And what I feel that I should talk is regarding a kind of various aspects related to the general science. You can say it is science with the society, science with the sustainability, or indirectly environment. So these three things, science, society, sustainability, or environment. So how they are interrelated and what we should understand from this. And little more things I will try to discuss. So whenever the word science comes in our mind, so we all feel that science means we are a scientist which should be perfect in a language known as English, and science means everything which is a Western word given, inventions, theories, and everywhere you will find the names of the English scientists. So that kind of setup, and even I am today speaking in English with you, and all this Punjab Science Congress you are holding, I suppose, I am not sure, in one known language, that is the English. So there are two aspects of this particular talk which I will be discussing. So whether everything has come out of India, either whatever Western model has been given or whatever is there in English or English journals, English literature, or English scientists, Newton, Galileo, and all that, Edison, and all, whether it is the only science. At that particular stage, we just forget to mention the ancient science, or more specifically, ancient Indian science, because the Western history is not very far, and that ancient Indian science is very, very important to understand, to learn. Let's say you say science. What is the technical meaning of science? Science, I will begin with why this is very important. Science, technical meaning word means is knowledge. If you go for dictionary, science means knowledge, to acquire knowledge, to explore everything. So in our system, in Indian system, I think everybody is knowing about Vedas. And the oldest written scripture is Vedas. And when I talk of this ancient Indian science, they feel that whether there was something science in India, no doubt India has a long culture, long history. There are civilization like Mahendragarh civilization. There are civilization of this in Pakistan, Mohenjo-daro, and all those kind of things. So, have you knowing the word meaning of Vedas? Vedas mean knowledge. So we feel that those Vedas are certain scriptures, certain religious books, certain kind of things where everything is there in Sanskrit, and Sanskrit is beyond our knowledge, beyond our understanding, and Sanskrit has something linked only with the ancient time. It is not relevant now. It means science which you use these days is practically Vedas. Original word Vedas. Vedas means science. And then we say that scientists are the real owners of the science, and they are the real scientists. And Vedas are written by rishis, munis, and those kind of things. They were not having any kind of knowledge, or they were not. So they were the scientists of that time. जिनको उस समय ऋषि बोला गया, उनको गुरु बोला गया, उनको, एंड वेदास के बाद जितने भी लिटरेचर लिखे गए, so they are all part of that. This is one aspect. And then, including Vedas, there was more development in this particular continent, Indian continent, Aryavrat जिसको बोल सकते, of the so many other parts of the sciences. और वेदास के बाद आप एस्ट्रोनॉमी की बात कर लो, स्पेस साइंस की बात कर लो, इन्वेंशंस की बात कर लो, they were all done by the Indians. The counting system is given by the India. The Rishi Bhaskaracharya, the development of zero. I will just mention these, otherwise these needs to be elaborated much more. The zero, the invention of zero, the invention of decimal, the value of pi. So the calculation, the movement of sun and all planets, 9 planets, Navgraha. So those aspects were already existing in our India. But only thing is we ourselves is not recognizing these things. We feel that these are only stories kind of things, and they are written in certain kind of religious books, and religion is something different than science, and science means everything which is modern, which is coming from Western. So just try to think. I just want to raise this activity in your mind. Then Kautilya, we feel that Kautilya was not a scientist. वो एक ऋषि मुनि था, उसने अपना एक अर्थशास्त्र दे दिया. So all scientific things are given in that Kautilya. How to do good agriculture, how to do good economy, जिसको आप broader science में लेके चलते. Then Ayurveda. I think this is a kind of ancient thing which is still relevant in modern, which cannot be denied even by the Western. Ayurveda, Charak Samhita, Sushrutu Samhita, they are two broad branches medicine and surgery, Sushruta Sanhita, and they have reported more than hundreds operations at that time with anesthesia and that kind of thing. And lot of instrumentation has been given by Sushruta, and even these things are being recognized in the Western world also. You can go any medical college. Viman Shastra, the history of those things which were mentioned in Ramayana or in Mahabharata, that they can fly, wahan pe viman the, and we were thinking, nee, they are only stories. Let me explain one more thing. Even if they were proven or not proven, you can just one part you can think they are the concepts were given by the Indians to fly. But more important is that the Wright brothers, before Wright brothers, there were certain persons in India, they tried to fly those aeroplanes, and they were taken by the Britishers, and then they got it a Nobel Prize by that. So these are all stories, I think they are there. You just try to put your mind, I am just holding. And there is one full granth on this Rishi Bharadwaj, Viman Shastra, all kind of Viman. तो यदि आप उसको नहीं भी मानना चाहते तो मैं कहता हूँ वो कॉन्सेप्ट्स भी आए, थ्योरीज भी आई. एक जीन थ्योरी की बात कई बार करते हैं जी, कौरव जो 100 लोग थे कौरव, तो वो जीन थ्योरी तभी चल पड़ी जब 100 कौरव की बात हो चुकी. 100 कौरव थे नहीं थे वो मैं डिस्कशन में, तो ये आपको सोचना पड़ेगा. द फाइट ऑफ महाभारत, जिसमें वो क्या कहते हैं जी, मिसाइल्स चली, वो तीरों के आगे आग लगी हुई थी, तीरों के आगे वो पानी बरसता था. व्हाट इज दिस? दीज आर ऑल मॉडर्न काइंड ऑफ प्रिसाइज वेपन्स, प्रिसीजन वेपन्स. तो आप अब भी नहीं मानो तो वो थ्योरीज भी किसने दी फिर, इसका मतलब. एंड दोज आर 5000 years बैक, महाभारत, रामायण. और एंड द काउंटिंग सिस्टम, जैसे मैं पहले बात कर रहा था, 0 seconds, उसके बाद, एंड डिस्टेंस ऑफ मून विद द अर्थ, अर्थ विद द मून, eclipses, जिसको आप कई बार एस्ट्रोनॉमी या हमारे जहाँ थोड़ा कहते थे ज्योतिष शास्त्र है जी, इनको क्या पता है जी, ये तो ऐसे ही लोगों को. So they have all scientific background, scientific systems were very much developed, and all major inventions were done in India. The electricity itself, ऋषि कन्वा, ये एडिसन का जो हम बल्ब कई बार देख लेते हैं, मैं तो कई बार हैरान हूँ भी, आप ये कैसे समझ सकते हैं कि न्यूटन को ध्यान में आया भी सेब गिरा था और उसने ही सोचा, इससे पहले दुनिया में सोचने वाले नहीं. And the law of gravity is written in Sanskrit literature. There are attraction forces in the earth which attracts you. So I think we should feel proud of our science, and we should not do the science in isolation. There we have a rich Indian science with us, and every aspect is very much, we need to find it and we need to brought it in front of the पहले तो अपने पास लाए फिर पब्लिक के पास लाए, and you will be more surprised. And all those foreigners, they are now taking much of your Sanskrit literature, much of your these books, and they are re-studying them, and they are reinventing them, the thought process. And we are following the Western principle. I'm not that there is not a conflict kind of thing. I'm just saying that we must begin with the total history of science, which starts from the Veda, which starts from the development of these civilizations. So I think this is one part. Second is the barriers of the language. Even I am speaking in English. I thought of starting with my own language, but I thought I don't know what kind of system is going on. So science only in English is a wrong step, wrong thought. Science or any education should be in the mother tongue, matra bhumi, maa boli. And we feel that you are having 23 states and every regional language is with Indian system. And we feel that we should only teach education and science in English. That is a wrong concept. Technically wrong. इसकी बात भी महाभारत से जुड़ती है, इसलिए मैं सोच रहा था भी मैं गल पंजाबी च करा, मैनूं लगा पता नहीं किन्ने जिहड़े सुनने वाले किन्ने जिहड़े समझण वाले आ। जे नहीं दिक्कत है पंजाबी च सुनो, विज्ञान जिहड़ा तुहाडी मां बोली च होना चाहिए। कोई भी मैं तो कहना एजुकेशन, और थैंक्स टू द न्यू एजुकेशन पॉलिसी मैं मिक्स कर लांगा गल, चलो किया गया इन्ने सालों बाद आके बई जिहड़ी प्राइमरी एजुकेशन है, मिडल एजुकेशन है, वो अपनी रीजनल लैंग्वेज हो। जे तुसीं बंगाल च रहिंदे हो बंगाली च पढ़ोगे, जे तुसीं तमिलनाडु च तमिल च पढ़ोगे, जे पंजाब च रहिंदे हो पंजाबी च पढ़ांगे। बट ਉਹਦਾ मतलब ये नहीं भी अंग्रेजी ਨੂੰ ਛੱਡ ਰਹੇ ਹਾਂ, ਉਹ ਇੰਟਰਨੈਸ਼ਨਲ ਲੈਂਗੁਏਜ ਹੈ ਉਹਦੇ ਚ। ਚਲੋ ਤੁਸੀਂ ਕਹੋਗੇ ਜੀ ਇਹ ਤੇ ਕੰਟਰੀ ਚ ਤੁਸੀਂ ਪੜ੍ਹਾ ਲਓਗੇ ਮਿਡਲ ਤੱਕ, ਤੇ ਸਾਇੰਸ ਤੇ ਜਾ ਕੇ ਜੇ ਰਿਸਰਚ ਕਰਨੀ ਹੈ, ਜੇ ਪੀਐਚਡੀ ਕਰਨੀ ਹੈ, ਜੇ ਜੀ ਐਮਫਿਲ ਕਰਨੀ ਹੈ, ਜੇ ਜੀ ਪੀਡੀਐਫ ਕਰਨੀ ਹੈ, ਜੇ ਡਿਗਰੀਆਂ ਲੈਣੀਆਂ, ਤੇ ਮੈਨੂੰ ਤੇ ਅੰਗਰੇਜ਼ੀ ਆਣੀ ਚਾਹੀਦੀ। And you must see the examples of China, Japan, German, French, और भी हो सकती कंट्री, वो सारे अपनी साइंस, अपनी हायर एजुकेशन, अपनी स्टडीज अपनी भाषावां च करा रहे। ਤੁਸੀਂ ਉਹਨਾਂ ਦੇ ਪੇਪਰ ਵੀ ਦੇਖੇ ਹੋਗੇ, ਜੇ ਸਟੂਡੈਂਟ ਜੁੜੇ ਨੇ, ਟੀਚਰ ਜੁੜੇ ਨੇ। ਦੋ ਕੰਟਰੀਜ਼ ਦਾ ਤੇ ਮੈਂ ਗਿਆ ਹਾਂ, ਚਾਈਨਾ ਤੇ ਜਾਪਾਨ ਦੇ ਵਿੱਚ। ਮੈਂ ਖੁਦ ਦੇਖਿਆ ਉਹ ਬੱਚੇ ਪੀਐਚਡੀ ਕਰ ਰਹੇ ਨੇ, ਦੇਖਿਆ ਕਿ ਉਹ ਸਾਰੀਆਂ ਆਪਣੀਆਂ ਸਾਇੰਸ ਦੇ ਪੇਪਰ, ਸਾਇੰਸ ਦੀ ਪ੍ਰੈਜੈਂਟੇਸ਼ਨ, ਪੀਪੀਟੀ, ਸਾਇੰਸ ਦੇ ਸਾਰੇ ਗੱਲ ਆਪਣੀ ਲੈਂਗੁਏਜ ਕਰ ਰਹੇ। ਚਾਈਨਾ ਚਾਈਨੀਜ਼ ਕਰ ਰਹੇ, ਜਾਪਾਨ ਜਾਪਾਨੀ। ਔਰ ਤੁਸੀਂ ਦੇਖਿਆ ਉਹ ਸਾਡੇ ਤੋਂ ਅੱਗੇ ਕਿੰਨੀ ਜ਼ਿਆਦਾ ਅੱਗੇ ਸਾਇੰਸ ਚ ਗਏ। ਸੋ ਇਹ ਕਨਸੈਪਟ ਨੂੰ ਠੀਕ ਕਰਨਾ ਵੀ ਕੋਈ ਵੀ ਜਿਹੜੀ ਸਿੱਖਣ ਵਾਲੀ ਚੀਜ਼ ਹੈ ਅੰਗਰੇਜ਼ੀ ਚ ਸਿੱਖੀ ਜਾ ਸਕਦੀ ਹੈ, ਸਪੈਸ਼ਲੀ ਸਾਇੰਸ, ਇਹ ਥੋੜਾ ਜਿਹਾ ਸਾਨੂੰ, ਮੈਂ ਤਾਂ ਅੱਜ ਗੱਲ ਕਰ ਰਿਹਾ ਕਿਉਂਕਿ ਵੀ ਆਰ ਆਲ ਸਾਇੰਟਿਸਟ ਜੁਆਇਨਡ ਹੇਅਰ, we are doing our wonderful research, but thought process should be broad, should be very elaborative. ਉਹਨੂੰ ਥੋੜਾ ਸਮਝਣਾ ਪਏਗਾ, ਉਹਨੂੰ ਠੀਕ ਕਰਨਾ ਪਏਗਾ, ਔਰ ਉਹਨੂੰ ਉਸ ਪਰਸਪੈਕਟਿਵ ਸੇ ਜੋੜਨਾ ਪਏਗਾ। ਉਹਨੂੰ ਤੇ ਤੁਸੀਂ ਕਹੋਗੇ ਜੀ ਹੋਰ ਇੱਕ ਜਿਹੜੀ ਮਹਾਭਾਰਤ ਨਾਲ ਗੱਲ ਜੁੜਦੀ ਵੀ ਜੇ ਅਸੀਂ ਕਹਿੰਦੇ ਅਸੀਂ ਤੇ ਬੱਚੇ ਨੂੰ ਕਹਿੰਦੇ ਕਿ ਪ੍ਰੈਗਨੈਂਸੀ ਜਾਂ ਬੱਚਾ ਪੇਟ ਚੋਂ ਸਿੱਖਦਾ, ਮਾਂ ਬੋਲੀ ਦਾ ਨਾਂ ਕਿੱਥੋਂ ਆਇਆ? ਉਹਨੂੰ ਪਿਤਾ ਬੋਲੀ ਕਿਉਂ ਨਹੀਂ ਕਿਹਾ ਗਿਆ? ਉਹਨੂੰ ਮਦਰ ਟੰਗ, ਫਾਦਰ ਟੰਗ ਕਿਉਂ ਨਹੀਂ ਕਿਹਾ ਗਿਆ? ਕਿਉਂਕਿ ਕਿਹਾ ਗਿਆ ਵੀ ਜਿਹੜਾ ਫੀਟਸ, ਜਿਹੜੀ ਫਰਟੀਲਾਈਜੇਸ਼ਨ ਹੋਏਗੀ, ਜਿਹੜਾ ਬੱਚਾ ਉਹਦੇ ਜੰਮੇਗਾ, ਉਹ ਉਸੇ ਸਮੇਂ ਲਰਨ ਕਰ ਰਿਹਾ। ਤੇ ਪਹਿਲੇ ਸਾਨੂੰ ਪੜਾਇਆ ਗਿਆ ਨਹੀਂ ਜੀ ਨਹੀਂ, ਇਹ ਤੇ ਐਵੇਂ ਕਲਪਨਾ ਨੇ, ਅਸੀਂ ਮਾਂ ਨੂੰ ਬੜਾ ਧਿਆਨ ਰੱਖਣਾ ਚਾਹੀਦਾ, ਫਲਾਣਾ ਕਰਨਾ ਚਾਹੀਦਾ। ਹੁਣ ਸਾਇੰਸ ਵੀ ਕਹਿ ਰਹੀ ਹੈ ਯੈਸ देयर शुड बी गुड एनवायरनमेंट अराउंड द प्रेग्नेंट वुमन, you should do music, you should do normal work, and that was given in Mahabharata when ਜਿਹੜਾ ਉਹ ਸੀ ਕੀ ਨਾਮ ਦਾ, ਜਿਹਨੇ ਚੱਕਰ ਤੋੜਿਆ ਸੀ, ਅਭਿਮਨਿਊ, ਉਹਨੇ ਪੂਰੀ ਕਹਾਣੀ ਕਿੱਥੇ ਸੁਣੀ ਸੀ? ਉਹਦੇ ਅੰਦਰ। ਅਸੀਂ ਕਹਿੰਦੇ ਜੀ ਇਹ ਝੂਠੀਆਂ ਕਹਾਣੀ ਦੱਸੋ, ਕੋਈ ਪੇਟ ਦੇ ਅੰਦਰ ਵੀ ਕੁਝ ਸਿੱਖ ਸਕਦਾ ਕੁਝ। ਸੋ ਮਦਰ ਦੀ ਜਿਹੜੀ ਅਟੈਚਮੈਂਟ ਹੈ ਉਹ ਫਰਟੀਲਾਈਜੇਸ਼ਨ ਤੋਂ ਬਾਅਦ ਸ਼ੁਰੂ ਹੋ ਜਾਂਦੀ, ਉਹ ਸਾਇੰਸ ਵੱਲੋਂ ਪ੍ਰੂਵ ਹੋ ਜਾਂਦੀ। ਫਿਰ ਤੁਸੀਂ ਕਹੋਗੇ ਨਹੀਂ ਜੀ ਨਹੀਂ, ਚਲੋ ਇਹ ਤੁਸੀਂ ਐਵੇਂ ਕਹਾਣੀ ਸੁਣਾਈ ਜਾਂਦੇ। ਫਿਰ ਜੇ ਤੁਸੀਂ ਆਪਣੇ ਸਾਇੰਟਿਸਟ ਦੇਖੋ, ਤੁਸੀਂ ਕਹਿੰਦੇ ਨਹੀਂ ਜਿਹੜਾ ਅੰਗਰੇਜ਼ੀ ਮੀਡੀਅਮ ਚ ਪੜ੍ਹੇਗਾ, ਅੰਗਰੇਜ਼ੀ ਸਾਇੰਸ ਕਰੇਗਾ, सीवी रमन, एपीजे अब्दुल कलाम, दो लोगों ने अपनी सारी प्राइमरी एजुकेशन ट्रेडिशनल सिस्टम च की है। साडे भी हो सकते, हरबिंद कौर राणा, अपने होर साइंटिस्ट हो सकते हैं। मैं पहले भी गल की जगदीश चंद्र बसु। सो लैंग्वेज जिहड़ी है, जिहड़ी अपनी मां बोली है, ਉਹਦੇ अंदर ਅਸੀਂ अपनी एजुकेशन कराइए, अपनी साइंस करिए। ਇਹ ਗੱਲ ਜਿਹੜੀ ਮੈਂ ਜੋੜੀ ਹੈ ਸੁਸਾਇਟੀ ਨਾਲ ਜੁੜਦੀ ਹੈ। ਸਾਇੰਸ ਤਾਂ ਹੀ ਸੁਸਾਇਟੀ ਨਾਲ ਜੁੜੇਗੀ ਜੇ ਇਹ ਦੋ ਗੱਲਾਂ ਕਰਾਂ, ਨਹੀਂ ਤਾਂ ਸੁਸਾਇਟੀ ਨਾਲ ਨਹੀਂ ਜੁੜੇਗੀ। ਕਹਿਣ ਨੂੰ ਕਹੀ ਜਾਂਦੇ ਆ ਸਾਇੰਸ, ਠੀਕ ਹੈ। ਇਹਦਾ ਕੀ ਮਤਲਬ ਹੈ? ਜਦੋਂ ਲੈਂਗੁਏਜ ਖੁੱਲੇਗੀ ਫਿਰ ਤੁਹਾਡੇ ਜਿਹੜਾ ਕੋਈ ਫਾਰਮਰ ਹੈ ਉਹ ਵੀ ਆਪਣੇ ਆਪ ਅੱਗੇ ਪ੍ਰੈਜ਼ੈਂਟ ਕਰ ਸਕਦੇ, ਤੇ ਉਹਨੂੰ ਵੀ ਕੋਈ ਆਈਡੀਆ ਆ ਸਕਦਾ। ਉਹ ਆਏਗਾ ਤੁਹਾਡੀ ਕਾਨਫਰੰਸ, ਤੁਸੀਂ ਉਹਨੂੰ ਬੁਲਾਓ, ਉਹਨੂੰ ਦੇਖੋ ਤੇ ਸੁਣੋ। ਕੋਈ ਆਰਟਿਸਟੀਅਨ ਹੈ, कोई होर डेवलपमेंट करता, कोई कारपेंटर है, कोई मेजन है, कोई मैकेनिक है, क्योंकि साइंस मीन्स साइंटिफिक माइंड। साइंस डज नॉट मीन पीएचडी, साइंस डज नॉट मीन मास्टर्स। सानू इंस्टीट्यूशन जो बाहर कढ़नी पेगी साइंस। कहने ਨੂੰ ਕਹੀ ਜਾਂਦੇ ਆ लैब टू अपना लैब टू लैंड, लैब टू दिस। प्रैक्टिकली की साडी ਜਿਹੜੀ ਇਨਵੈਂਸ਼ਨ ਹੈ ਉਹ ਗੱਲ ਜਿਹੜੀ ਬਣਾਈ ਹੁੰਦੀ ਉਹ ਚੱਲ ਜਾਂਦੀ ਹੈ, ਪਰ ਸਾਇੰਸ ਨਾਲ ਅਸੀਂ ਨਹੀਂ ਜੁੜਦੇ। तो मेरी हाथ जोड़ के प्रार्थना है, और खास तौर पे पंजाब साइंस कांग्रेस से मैं बोल रहे हैं ਜਿਹਦਾ ਨਾਂ ਹੀ ਪੰਜਾਬ ਸਾਇੰਸ ਕਾਂਗਰਸ ਹੈ। ਤੇ ਜੇ ਅਸੀਂ ਪੰਜਾਬੀ 'ਚ ਵਿਗਿਆਨ ਨਹੀਂ ਕਰਾਂਗੇ, ਕਹਿੰਦੇ ਨਹੀਂ ਸਕੂਲ ਵਾਲੇ ਕਰਨਗੇ ਜੀ, ਮੈਂ ਤਾਂ ਕਹਿੰਦਾ ਸਕੂਲ ਵਾਲਿਆਂ ਨੇ ਛੱਡ ਦਿੱਤਾ ਅੱਜ ਤੱਕ। ਸੋ ਸਾਇੰਸ ਮੀਨਸ ਸਾਇੰਟਿਫਿਕ ਟੈਂਪਰਾਮੈਂਟ। ਸਾਇੰਸ ਨੂੰ ਬ੍ਰੌਡ ਸੈਂਸ ਲੈਣਾ, ਸੋਸਾਇਟੀ ਵਾਸਤੇ ਲੈਣਾ, ਔਰ ਇੱਕ ਮਾਡਲ ਤੋਂ ਹਟ ਕੇ ਪੁਰਾਣੇ ਸਾਇੰਸ ਦੀ ਗੱਲ ਕਰਨੀ, ਇਹ ਮੇਰੀ ਰਿਕੁਐਸਟ ਹੈ ਔਰ ਇਹ ਮੇਰੀ ਪ੍ਰਾਰਥਨਾ ਹੈ ਸਾਰਿਆਂ ਦੇ ਅੱਗੇ। ਮੈਨੂੰ ਲੱਗਦਾ ਵੀ ਇਹ ਗੱਲ ਸਾਡੇ ਸਮਝ ਆਏਗੀ, ਅਸੀਂ ਉਹਨੂੰ ਜ਼ਰੂਰ ਕਰਾਂਗੇ। ਤਾਂ ਬਹੁਤਾ ਲੰਬਾ ਨਾ ਕਰਦੇ ਹੋਏ, ਇਹਦੇ 'ਚ ਹੋਰ ਵੀ ਆਸਪੈਕਟਸ ਜੁੜ ਸਕਦੇ ਨੇ, ਬਟ ਇਹ ਤਾਂ ਹੀ ਸੋਸਾਇਟੀ ਦਾ ਸੁਧਾਰ ਹੋ ਸਕਦਾ। ਹੁਣ ਇਹਦੇ ਨਾਲ ਦੋ ਤਿੰਨ ਗੱਲਾਂ ਛੋਟੀਆਂ ਜੋੜ ਕੇ, ਇੱਕ ਇਨਵਾਇਰਨਮੈਂਟ ਦੀ ਗੱਲ, ਕਿਉਂਕਿ ਮੇਰਾ ਵਿਸ਼ਾ ਹੈ ਇਨਵਾਇਰਨਮੈਂਟ ਦਾ। ਮੈਂ ਤਾਂ ਹੀ ਦੇਖਿਆ ਵੀ ਜੇ ਇਹ ਪ੍ਰੋਬਲਮ ਆਈ ਵੀ ਅਸੀਂ ਸਾਇੰਸ ਨੂੰ ਅੰਗਰੇਜ਼ੀ ਨਾਲ, ਵੈਸਟਰਨ ਵਰਡ ਨਾਲ ਜੋੜ ਰਿਹਾ ਔਰ ਟੈਕਨੋਲੋਜੀ ਨਾਲ ਜੋੜ ਰਿਹਾ, ਤੇ ਕੀ ਹੋਇਆ ਵੀ ਅਸੀਂ ਇਨਵਾਇਰਨਮੈਂਟ ਨੂੰ ਭੁੱਲ ਗਏ। ਮੈਨੂੰ ਬਹੁਤ ਘੱਟ ਸਮਝ ਆਉਂਦਾ ਵੀ ਜਿਹੜੀ ਸਾਇੰਸ ਹੈ ਉਹ ਇਨਵਾਇਰਨਮੈਂਟ ਪ੍ਰੋਟੈਕਸ਼ਨ 'ਚ ਕੰਮ ਆ ਰਹੀ ਹੈ। ਵੀ ਆਰ ਡਿਵੈਲਪਿੰਗ ਨਿਊ ਐਂਡ ਨਿਊ ਟੈਕਨੋਲੋਜੀ। ਲੈਟਸ ਸੇ ਆਰਓ ਡਿਵੈਲਪ ਕਰ ਦਿੱਤਾ, ਅਸੀਂ ਪਲਾਸਟਿਕ ਡਿਵੈਲਪ ਕਰ ਲਿਆ, ਅਸੀਂ ਹੋਰ ਇਹੋ ਜਿਹੀਆਂ ਚੀਜ਼ਾਂ ਡਿਵੈਲਪ ਕਰਨੀਆਂ, ਨੈਨੋ ਟੈਕਨੋਲੋਜੀ ਬਣਾ ਲਈ, ਪਰ ਵਿਦਾਊਟ ਟੇਕਿੰਗ ਕੇਅਰ ਆਫ ਦ ਇਨਵਾਇਰਨਮੈਂਟ। ਗ੍ਰੀਨ ਰੈਵੋਲੂਸ਼ਨ ਲੈ ਦਿੱਤੀ, ਕੈਮੀਕਲ ਪੈਸਟੀਸਾਈਡ ਬਣਾ ਲਏ, ਬੜਾ ਕੁਝ ਬਣਾ ਲਿਆ, ਈਵਨ ਵੈਪਨਸ ਬਣਾ ਲਏ, ਹੋਰ ਚੀਜ਼ਾਂ ਡਿਵੈਲਪਮੈਂਟ ਕਰ ਦਿੱਤੀ। ਮੈਂ ਤੇ ਕਹਿੰਦਾ ਮਤਲਬ ਜੈਨੇਟਿਕਲ ਲੈਬ, DNA ਲੈਬ, ਜੈਨੇਟਿਕਲ ਮੋਡੀਫਾਈਡ ਆਰਗੇਨਿਜ਼ਮਸ, BT ਕਾਟਨ, ਸਾਰਾ ਕੁਝ ਬਣਾ ਲਿਆ, ਇੰਟੈਂਸਿਵ ਐਗਰੀਕਲਚਰ ਨਾਂ ਦੇ ਦਿੱਤਾ। ਆਲ ਸਾਇੰਸ। ਥੋੜਾ ਜਿਹਾ ਸਾਇੰਸ ਵਾਲਿਆਂ ਨੂੰ ਸੋਚਣਾ ਪਏਗਾ ਕਿ ਕਿਆ ਮੇਰੀ ਸਾਇੰਸ ਦੀ ਜਿਹੜੀ ਮੈਂ ਇਨੋਵੇਸ਼ਨ ਕਰ ਰਿਹਾ ਜਾਂ ਸਾਇੰਸ ਕਰ ਰਿਹਾ, ਵੀ ਇੰਨੀ ਡੇਂਜਰਸ ਤੇ ਨਹੀਂ ਹੋ ਰਹੀ। ਮੈਂ ਆਈ ਐਮ ਗੋਇੰਗ ਅਗੇਂਸਟ ਦਾ ਲਾਅ ਆਫ ਨੇਚਰ। ਜੇ ਮੇਰੇ ਨਾਲ ਪੁੱਛੋ ਤੇ ਜੈਨੇਟਿਕਲੀ ਮੋਡੀਫਾਈਡ ਉਹ ਅੰਗਰੇਜ਼ ਨੇਚਰ ਦੇ ਲਾਅ ਤੋਂ ਅਸੀਂ ਇੱਕ ਜੀਨ ਬੈਕਟੀਰੀਆ ਦਾ ਕੱਢ ਕੇ ਹਿਊਮਨ 'ਚ ਪਾ ਰਹੇ, ਸੌਰੀ ਪਲਾਂਟਸ 'ਚ ਪਾ ਰਹੇ, ਐਨੀਮਲ 'ਚ ਪਾ ਰਹੇ। ਦਿਸ ਇਜ਼ ਨੇਚਰ ਅਲਾਉ ਯੂ ਟੂ ਹਾਈਬ੍ਰਿਡ, ਨੇਚਰ ਪ੍ਰਮੋਟ ਕ੍ਰਾਸਿੰਗ, ਬਟ ਉਹ ਕ੍ਰਾਸਿੰਗ ਨਹੀਂ ਹੈ ਵੀ ਇੱਕ ਮਤਲਬ ਸਪੀਸ਼ੀਜ਼ ਟੂ ਸਪੀਸ਼ੀਜ਼ ਹੋ ਸਕਦੀ ਹੈ, ਵੈਰਾਈਟੀ ਟੂ ਵੈਰਾਈਟੀ ਹੋ ਸਕਦੀ ਹੈ, ਪਰ ਜੀਨਸ ਟੂ ਜੀਨਸ, ਮੈਂ ਕਹਿੰਦਾ ਕਿੰਗਡਮ ਟੂ ਕਿੰਗਡਮ, ਮਤਲਬ ਇੱਕ ਆਲ ਟੂਗੇਦਰ, ਉਹ ਬਹੁਤ ਡੇਂਜਰਸ ਕੰਮ। ਸੋ ਪਰਮਾਤਮਾ ਦਾ ਮਤਲਬ ਮੇਰੇ ਜੋ ਸਮਝ ਆਉਂਦਾ ਹੈ ਵੀ ਅਸੀਂ ਇਹੋ ਜਿਹੀ, ਔਰ ਮੈਂ ਤੇ ਕਈ ਵਾਰੀ ਇਹ ਮੰਨਣਾ ਵੀ ਜੇ ਕਰੋਨਾ ਨਿਕਲਿਆ ਜਾਂ ਵਾਇਰਸ ਨਿਕਲਿਆ, ਇਹ ਤਾਂ ਹੀ ਨਿਕਲ ਕੇ ਆਇਆ ਵੀ ਅਸੀਂ ਮਤਲਬ ਜੀਨ ਲੈਵਲ ਤੇ ਚਲੇ ਗਏ, ਵਾਇਰਸ ਲੈਵਲ ਤੇ ਚਲੇ ਗਏ। ਹਾਂ ਸਟੱਡੀ ਕਰਨਾ ਜ਼ਰੂਰੀ ਹੈ, ਬਟ ਇੰਨੀਆਂ ਚੀਜ਼ਾਂ ਸਾਰਾ ਕੁਝ ਉਹਨਾਂ ਕੋਲ ਲੱਭੀ ਜਾਵਾਂਗੇ ਤੇ ਬਹੁਤ ਡੇਂਜਰਸ ਹੋ ਜਾਏਗਾ। ਸੋ ਉਹ ਥੋੜਾ ਜਿਹਾ ਧਿਆਨ ਰੱਖਣ ਦੀ ਗੱਲ ਹੈ ਵੀ ਕੋਈ ਟੈਕਨੋਲੋਜੀ ਅਸੀਂ ਬਣਾ ਰਹੇ ਹਾਂ, ਕੋਈ ਸਿਸਟਮ ਅਸੀਂ ਬਣਾ ਰਹੇ ਹਾਂ ਸਾਇੰਸ ਦਾ, ਜਾਂ ਕਿਆ ਉਹਦੇ ਨਾਲ ਇਨਵਾਇਰਨਮੈਂਟ ਬਚ ਰਿਹਾ ਕਿ ਇਨਵਾਇਰਨਮੈਂਟ ਖਰਾਬ ਹੋ। ਕਹਿਣ ਨੂੰ ਅਸੀਂ ਇੱਕੋ ਟੈਕਨੋਲੋਜੀਜ਼ ਬਾਕੀ ਨਾਂ ਲੈ ਦਿੰਦੇ ਹਾਂ, ਬਟ ਪ੍ਰੈਕਟੀਕਲੀ ਨਹੀਂ। ਮੈਂ ਤਾਂ ਮੈਂਸ਼ਨ ਕੀਤਾ ਹੈ ਕਿਉਂਕਿ ਮੇਰਾ ਕੰਮ ਹੈ ਗੰਡੋਇਆਂ ਤੇ, ਕੇਚੂਆਂ ਤੇ ਅਰਥਵਰਮ। ਹੁਣ ਅਰਥਵਰਮ ਇਕੋਲੋਜੀਕਲ ਇੰਜੀਨੀਅਰਸ ਨੇ, ਅਸੀਂ ਉਹਨਾਂ ਨੂੰ ਛੱਡ ਦਿੱਤਾ, ਅਸੀਂ ਹੋਰ ਤਰ੍ਹਾਂ ਦੀ ਇੰਜੀਨੀਅਰਿੰਗ ਸ਼ੁਰੂ ਕਰ ਦਿੱਤੀ ਵੀ ਸੀਵਰੇਜ ਟ੍ਰੀਟਮੈਂਟ ਪਲਾਂਟ, ਇਹ ਉਹ ਸਾਰਾ ਲਗਾ ਕੇ ਅਸੀਂ ਠੀਕ ਕਰਾਂਗੇ। ਇਹ ਚੀਜ਼ਾਂ ਆਰਓ ਸਿਸਟਮ ਨੇ, ਇਹ ਲਿਮਿਟਸ ਵਾਸਤੇ ਬਣੀਆਂ ਸੀ, ਅਸੀਂ ਅਨਲਿਮਿਟਡ ਉਹਨੂੰ ਯੂਜ਼ ਕਰਦੇ। ਸੋ ਥੋੜਾ ਜਿਹਾ ਧਿਆਨ ਰੱਖਣਾ, ਉਹਦਾ ਰਸਤਾ ਵੀ ਹੈਗਾ। ਇਨਵਾਇਰਨਮੈਂਟ ਇੰਨਾ ਭਰਿਆ ਪਿਆ, ਅਸੀਂ ਉਹੋ ਜਿਹੀ ਸਾਇੰਸ ਕਰੀਏ ਜਿਹੜੀ ਬਾਇਓਡਾਇਵਰਸਿਟੀ ਨੂੰ ਪ੍ਰੋਟੈਕਟ ਕਰੇ, ਜਿਹੜੇ ਸਾਡੇ ਪਲਾਂਟਸ ਨੂੰ, ਫਲੋਰਾ ਨੂੰ, ਫੋਨਾ ਨੂੰ, ਰਿਵਰਸ ਨੂੰ, ਬਾਇਓ ਰਿਸੋਰਸ ਨੂੰ ਬਚਾ ਕੇ ਰੱਖੇ। ਉਹ ਵੀ ਭਾਰਤ ਨੇ ਦੱਸਿਆ ਸੀ, ਇੰਡੀਆ ਨੇ ਦੱਸਿਆ ਸੀ ਵੀ ਅਸੀਂ ਨੇਚਰ ਦੀ ਵਰਸ਼ਿਪ ਕਰਨੀ। ਵਰਸ਼ਿਪ ਦਾ ਮਤਲਬ ਉਹਨਾਂ ਨੂੰ ਪ੍ਰੋਟੈਕਟ ਕਰਕੇ ਰੱਖਣਾ ਹੈ। ਪਵਨ ਗੁਰੂ ਪਾਣੀ ਪਿਤਾ ਮਾਤਾ ਤੱਕ ਅਸੀਂ ਉਹ ਟੈਕਨੀਕਲੀ ਪ੍ਰੋਟੈਕਟ ਨਹੀਂ ਕਰ ਸਕੇ, ਉਹ ਸਗੋਂ ਖਰਾਬ ਹੁੰਦੇ ਪਏ। ਹਾਂ ਖਰਾਬ ਤਾਂ ਪਹਿਲੇ ਕਹਿੰਦੇ ਪਾਣੀ ਖਰਾਬ ਹੋ ਗਿਆ, ਹਵਾ ਖਰਾਬ ਹੋ ਗਈ, ਫਲਾਣਾ ਸੋਇਲ ਖਰਾਬ ਹੋ ਗਿਆ, ਫਿਰ ਕਹਿੰਦੇ ਟੈਕਨੋਲੋਜੀ ਲਿਆਓ ਠੀਕ ਕਰ ਦਿਓ। ਅਰੇ ਭਈਆ, ਜਿਹੜੀ ਆਕਸੀਜਨ ਪਲਾਂਟ ਦੇ ਸਕਦਾ, ਆਕਸੀਜਨ ਸਿਲੰਡਰ ਨਹੀਂ ਦੇ ਸਕਦਾ। ਜਿਹੜੀ ਕੁਦਰਤੀ ਤੌਰ ਤੇ ਰੇਨ ਆਉਂਦੀ ਹੈ, ਜਿਹੜੀ ਪਾਣੀ ਨੂੰ ਸਾਫ਼ ਕਰਕੇ ਜ਼ਮੀਨ ਤੋਂ ਲਿਜਾਂਦੀ ਹੈ, ਫਿਰ ਤੁਹਾਨੂੰ ਵਾਪਸ ਦਾ ਫਰੈਸ਼ ਫਾਰਮ ਆਫ ਵਾਟਰ ਇਜ਼ ਓਨਲੀ ਰੇਨ ਵਾਟਰ। ਉਹਨੂੰ ਸੰਭਾਲਣਾ, ਉਹਨੂੰ ਬਚਾਉਣਾ, ਉਹਨੂੰ ਧਰਤੀ ਦੇ ਅੰਦਰ ਰੱਖਣਾ, ਉਹੀ ਟੈਕਨੋਲੋਜੀ। ਆਰਓ ਲਗਾ ਕੇ ਬਾਕੀ ਜਾਂ ਫਿਲਟਰ ਹੋ ਸਕਦਾ ਛੋਟਾ ਮੋਟਾ ਲੱਗ ਜਾਏ, ਤਾਂ ਲੱਗਣਾ ਚਾਹੀਦਾ ਜਿੱਥੇ ਥੋੜੀ ਦਿੱਕਤ। ਹਰ ਜਗ੍ਹਾ ਚੀਜ਼ਾਂ ਘਰ ਘਰ ਤੇ ਲੱਗ ਜਾਂਦੀਆਂ ਤੇ ਇਹ ਟੈਕਨੋਲੋਜੀ ਦੀ ਮਿਸਯੂਜ਼, ਇਨਵਾਇਰਨਮੈਂਟ ਖਰਾਬ। ਇਹ ਥੋੜਾ ਜਿਹਾ ਮੇਰੇ ਮਨ ਚ ਆਉਂਦਾ ਹੈ ਵੀ ਉਹਨੂੰ ਇਹੋ ਜਿਹੀਆਂ ਚੀਜ਼ਾਂ ਬਣਾਈਏ ਜਿਹਦੇ ਨਾਲ ਵਿਗਿਆਨ ਜਿਹੜਾ, ਸਾਇੰਸ ਜਿਹੜੀ ਹੈ ਜਾਂ ਕੋਈ ਵੀ ਨਵੀਂ ਇਨਵੈਂਸ਼ਨ ਹੈ ਟੈਕਨੋਲੋਜੀ, ਕਿਤੇ ਇਨਵਾਇਰਨਮੈਂਟ ਖਰਾਬ ਨਹੀਂ। ਲੌਂਗ ਟਰਮ, ਸ਼ਾਰਟ ਟਰਮ ਤੁਸੀਂ ਦਿਖਾ ਸਕੋਗੇ ਜੀ। ਹੁਣ ਕਈ ਵਾਰੀ ਮੇਰੇ ਸਾਹਮਣੇ ਆਉਂਦਾ ਜੀ ਫਿਲਟਰ ਲਾ ਰਹੇ ਜੀ, 에ਅਰ ਫਿਲਟਰ ਲਾ ਰਹੇ। ਅਰੇ ਪਹਿਲੇ 에ਅਰ ਖਰਾਬ ਹੀ ਨਾ ਕਰੋ, ਅਸੀਂ ਮਿਨੀਮਾਈਜ਼ ਕਰੀਏ ਪੋਲਿਊਸ਼ਨ ਦੇ ਸੋਰਸਸ। ਸੋ ਇਸ ਤਰ੍ਹਾਂ ਦੀ ਟੈਕਨੋਲੋਜੀਜ਼ ਨਾਲ ਗੱਲ ਕਰੀਏ, ਉਹੋ ਜਿਹੇ ਇਕੋ ਫਰੈਂਡਲੀ ਜਿਹੜੀਆਂ ਚੀਜ਼ਾਂ ਬਣਾਈਏ। ਬਾਇਓਲੋਜੀਕਲ ਸਿਸਟਮ, ਨੇਚਰ ਦੇ ਵਿੱਚ ਬਹੁਤ ਕੁਝ ਹੈ। ਮੈਂ ਕਹਿੰਦਾ ਨਵੇਂ ਬੈਕਟੀਰੀਆ, ਨਵੇਂ ਵਾਇਰਸ ਬਣਾਉਣ ਨਾਲੋਂ ਜਿਹੜੇ ਆਲਰੇਡੀ ਐਗਜ਼ਿਸਟਿੰਗ ਨੇ, ਤੁਸੀਂ ਨੇਚਰ ਨੂੰ ਪਾਰ ਨਹੀਂ ਕਰ ਸਕਦੇ। ਉਹਨਾਂ 'ਚ ਇੰਨਾ ਪੋਟੈਂਸ਼ੀਅਲ ਹੈ, ਉਹਨਾਂ ਨੂੰ ਯੂਜ਼ ਕਰੀਏ। ਸਿੰਥੈਟਿਕ ਕੰਪਾਊਂਡ ਬਣਾਉਣਾ ਸ਼ੁਰੂ ਕਰਤਾ, ਸਿੰਥੈਟਿਕ ਮੋਲੀਕੂਲਸ ਬਣਾਉਣੇ ਸ਼ੁਰੂ ਕਰਤੇ, ਸਿੰਥੈਟਿਕ ਆਰਗੇਨਿਜ਼ਮ ਬਣਾਉਣੇ ਸ਼ੁਰੂ ਕਰਤੇ। ਅਰੇ ਜਿਹੜਾ ਨੇਚਰ 'ਚ ਹੈ ਉਹਨੂੰ ਯੂਟਿਲਾਈਜ਼ ਕਰੀਏ। ਅਰਥ ਫਾਰਮ ਤੁਸੀਂ ਦੇਖੋ, ਜੇ ਕਿਸੇ ਨਾਲ ਲੰਬੇ ਟਾਈਮ ਤੇ ਗੱਲ ਕਰਨੀ ਹੋਗੀ ਜਾਂ ਮੋਸਟ ਵੈਲਕਮ, ਉਹ ਮਤਲਬ ਦੁਨੀਆ ਦੀ ਵੇਸਟ ਮੈਨੇਜਮੈਂਟ ਉਹ ਕਰਦਾ ਪਿਆ ਸੀ। ਅਸੀਂ ਚੁੱਕ ਕੇ ਉਹਨੂੰ ਖੇਤਾਂ 'ਚੋਂ ਖੇਤੀ ਉਹ ਕਰਦਾ ਪਿਆ ਸੀ, ਫਾਰਮਰਸ ਫਰੈਂਡ ਉਹ ਸੀ, ਅਸੀਂ ਚੁੱਕ ਕੇ ਕੈਮੀਕਲ ਪਾ ਤੇ ਉਹ ਭੱਜ ਗਿਆ। ਉਹ ਸਾਰਾ ਸੋਲਿਡ ਵੇਸਟ ਮੈਨੇਜਮੈਂਟ ਕਰ ਸਕਦਾ, ਉਹਦੇ ਕੋਲ ਹੋਰ ਕੋਈ ਕੰਮ ਨਹੀਂ, ਉਹ ਤੁਹਾਨੂੰ ਮੈਨਿਓਰ ਦੇਗਾ, ਅਸੀਂ ਉਹਨੂੰ ਭੁੱਲ ਗਏ। ਸੋ ਇਸ ਤਰ੍ਹਾਂ ਦੀ ਗੱਲਾਂ ਨੇ। ਸੋ ਲਾਸਟ ਇਨਵਾਇਰਨਮੈਂਟ ਸੁਸਾਇਟੀ ਦੀ ਗੱਲ ਤਾਂ ਕਰਦੇ ਹੋਏ ਵੀ ਜੇ ਸਾਇੰਸ ਨੂੰ ਸੁਸਾਇਟੀ 'ਚ ਲਿਆਉਣਾ ਇਕੱਲੇ ਲੈਕਚਰ, ਔਰ ਮੈਨੂੰ ਖੁਸ਼ੀ ਹੈ ਵੀ ਡਾਕਟਰ ਬਾਠ ਵੀ ਬੈਠੇ ਨੇ, ਸਟੇਟ ਕਾਉਂਸਲ ਜਿਹੜੀ ਹੈ ਇੱਕ ਆਜ਼ਾਦੀ ਦਾ ਮਹੋਤਸਵ ਪੇਸ਼ ਕਰ ਰਹੀ ਹੈ, ਔਰ ਸਾਇੰਸ ਸਰਵਤਰ ਵਰਜਿਤ ਜਿਹੜੀ ਹੈ ਵੀ ਵਿਗਿਆਨ ਜੈ ਕਿਸਾਨ ਹੈ ਜੀ, ਗੱਲਬਾਤ ਕਰਨੀ ਪਰ ਉਹ ਪ੍ਰੈਕਟੀਕਲੀ ਤਾਂ ਹੀ ਆਏਗੀ ਜੀ ਸੁਸਾਇਟੀ ਨਾਲ ਜੁੜਾਂਗੇ, ਵਿਗਿਆਨ ਨੂੰ ਜੋੜਾਂਗੇ, ਲੈਂਗੁਏਜਸ ਦੇ ਬੈਰੀਅਰ ਤੋੜਾਂਗੇ, ਹੋਰ ਵੀ ਬੜੇ ਬੈਰੀਅਰਸ ਨੇ ਉਹ ਤੋੜਾਂਗੇ। ਫਿਰ ਇਹਦੇ ਨਾਲ ਇੱਕ ਛੋਟੀ ਜਿਹੀ ਹੋਰ ਗੱਲ ਕਰਕੇ ਵੀ ਵਿਗਿਆਨਿਕ ਵੀ ਪੜ੍ਹਨੇ ਚਾਹੀਦੇ, ਵਿਗਿਆਨਿਕਾਂ ਦਾ ਜੀਵਨ ਵੀ ਪੜ੍ਹਨਾ ਚਾਹੀਦਾ। ਮੈਂ ਸੀ ਵੀ ਰਮਨ ਦੀ ਸਾਇੰਸ ਡੇ ਆ ਰਿਹਾ, ਉਹ ਆਜ਼ਾਦੀ ਦਾ ਮਹੋਤਸਵ ਜਿਹਦੀ ਗੱਲ ਆਈ ਕਿੱਥੋਂ ਆਈ? ਦੇਖੋ, ਅਸੀਂ ਕਦੀ ਸੋਚਿਆ ਸੀ ਵੀ ਜਿਹੜੇ ਸਾਇੰਟਿਸਟ ਨੇ ਉਹਨਾਂ ਨੇ ਵੀ ਆਜ਼ਾਦੀ ਦੇ ਵਿੱਚ ਹਿੱਸਾ ਲਿੱਤਾ ਹੋਏਗਾ? ਜੇਸੀ ਬਸੂ ਨੇ ਤਨਖਾਹ ਲੈਣੀ ਮਨਾ ਕਰ ਦਿੱਤੀ ਸੀ, ਉਹ ਕਹਿੰਦੇ ਜੀ ਮੈਨੂੰ ਅੰਗਰੇਜ਼ਾਂ ਨਾਲ ਵੱਖਰੀ ਤਨਖਾਹ ਦਿਓਗੇ, ਮੈਂ ਵੀ ਉਹਨਾਂ ਵਿਗਿਆਨਿਕ ਹੈ। ਉਹਦੀ ਕਿਤਾਬ ਚੁੱਕ ਕੇ ਲੋਕਾਂ ਨੇ ਦੂਸਰੀ, ਉਹਨੇ ਮਾਰਕੋਨੀ ਨੇ ਆਪਣੇ ਨਾਂ ਤੇ ਨੋਬਲ ਪ੍ਰਾਈਜ਼ ਦਿੱਤੇ। ਔਰ ਸਾਡੇ ਹਿੰਦੁਸਤਾਨ 'ਚ ਕਦੀ ਵੀ ਪੇਟੈਂਟ ਜੇ ਉਹ ਕਰਾਉਣ ਦੀ ਪਰੰਪਰਾ ਨਹੀਂ। ਜਦੋਂ ਵੇਦ ਲਿਖੇ ਗਏ, ਰਿਸ਼ੀ ਮੁਨੀਆਂ ਨੇ ਗੱਲ ਕੀਤੀ, ਉਹਨੇ ਕਿਹਾ ਸੁਸਾਇਟੀ ਵਾਸਤੇ ਹੈ। ਔਰ ਮੈਂ ਇਹਦੇ 'ਚ ਵੀ ਜਿਹੜਾ ਵੀ ਇਨਵਾਇਰਨਮੈਂਟ ਦੇ ਜਿਹੜੇ ਅਸੀਂ ਵਿਗਿਆਨਿਕ ਹੈ ਜਾਂ ਦੂਸਰੇ, ਉਹਦੇ ਨਾਲ ਚੰਗਾ ਤੁਸੀਂ ਦੇਖੋ ਸਿੰਚੇਵਾਲ ਜੀ ਕੰਮ ਅੱਛਾ ਕਰ ਰਹੇ ਨੇ, ਭਗਤ ਪੂਰਨ ਸਿੰਘ ਜੀ ਨੇ ਵਿਗਿਆਨ ਇਨਵਾਇਰਨਮੈਂਟ ਦੀ ਗੱਲ ਕੀਤੀ। ਸੋ ਕਈ ਵਾਰੀ ਵਿਗਿਆਨਿਕਾਂ ਤੋਂ ਵੀ ਜਿਹੜੇ ਸੰਤ ਨੇ, ਜਿਹੜੇ ਠੀਕ ਨੇ, ਜਿਨ੍ਹਾਂ ਨੇ ਉਹ ਸਮਾਜ ਨੂੰ ਸਮਝ, ਥਾਟ ਪ੍ਰੋਸੈਸ ਠੀਕ ਹੋਣਾ ਚਾਹੀਦਾ। ਸੋ ਵਿਗਿਆਨਿਕਾਂ ਦੇ ਜੀਵਨ ਵੀ ਪੜ੍ਹਨੇ ਬਹੁਤ ਜ਼ਰੂਰੀ ਹੈ, ਇਹ ਮੇਰਾ ਕਹਿਣ ਦਾ ਮਤਲਬ। ਔਰ ਇੰਡੀਅਨ ਵਿਗਿਆਨਿਕਾਂ ਦੇ ਜੀਵਨ ਪੜ੍ਹੋ, ਔਰ ਉਹਨਾਂ ਨੇ ਮਤਲਬ ਸਾਇੰਸ ਦੀ ਕੰਟਰੀਬਿਊਸ਼ਨ ਦੇ ਨਾਲ ਨਾਲ ਸੋਸਾਇਟੀ 'ਚ ਵੀ ਕੰਟਰੀਬਿਊਟ ਕੀਤਾ। ਉਹਨਾਂ ਨੇ ਕਦੀ ਵੀ ਨੇਮ ਔਰ ਫੇਮ ਵਾਸਤੇ ਕੰਮ ਨਹੀਂ। ਸੋ ਲਾਸਟ ਗੱਲ ਮੈਂ ਜੋੜ ਕੇ ਆਪਣੀ ਗੱਲ ਖਤਮ ਕਰਾਂਗਾ। ਹੁਣ ਅਸੀਂ ਵੀ ਕੀ ਕਰ ਰਹੇ ਹਾਂ, ਜਿਹੜੇ ਜੁੜੇ ਸਾਰੇ ਲੋਕ, ਮੇਰਾ ਜੀ ਇੱਕ ਇਸ਼ੂ ਆ ਗਿਆ ਸਾਇੰਸ ਤੇ ਕੈਰੀਅਰ, ਸ਼ਾਇਦ ਇਹਨੂੰ ਕਹਿ ਲਓ ਤੁਸੀਂ। ਸਿਸਟਮਸ ਯੂਨੀਵਰਸਿਟੀਜ਼ ਦੇ, ਕਾਲਜਸ ਦੇ, ਮਤਲਬ ਜੋ ਮੇਰਾ ਐਨਾਲਿਸਿਸ ਵਰਕ ਹੈ, ਮੈਂ ਡਿਫਰ, ਅੱਜ ਮੇਰਾ ਮੌਕਾ ਮੈਂ ਗੱਲ ਕਰਕੇ ਵੀ ਅਸੀਂ ਸਾਇੰਸ ਨੂੰ ਵੀ ਮਟੀਰੀਅਲਾਈਜ਼ ਕਰ ਦਿੱਤਾ ਹੈ ਜੀ। ਜਿਹੜਾ ਕੋਈ ਪਬਲਿਸ਼ ਕਰੇਗਾ, ਜਿਹੜਾ ਕੋਈ ਇੰਪੈਕਟ ਫੈਕਟਰ ਜਾਊਗਾ, ਜਿਹਦੀ ਕੋਈ ਸਾਈਟੇਸ਼ਨ ਵਧੇਗੀ, ਮੇਰੇ ਬਾਰੇ ਵੀ ਬੜਾ ਮਤਲਬ ਬਾਇਓਡਾਟਾ ਪੜ੍ਹਿਆ ਗਿਆ। ਬਟ ਮੈਨੂੰ ਲੱਗਦਾ ਵੀ ਵਿਗਿਆਨ ਨੂੰ ਜੋੜਨ ਨਾਲ ਹੀ ਇਹ ਚੀਜ਼ ਨਹੀਂ ਠੀਕ। ਹਾਂ, ਉਹ ਕੀ ਕਰ ਰਿਹਾ, ਕਿਹੜਾ ਕੰਮ ਕਰ ਰਿਹਾ, ਉਹ ਜ਼ਰੂਰ ਹੋਣਾ ਚਾਹੀਦਾ। ਪਰ ਫਿਰ ਕੀ ਹੋ ਰਿਹਾ, ਉਹ ਸਾਰੇ ਦੁਨੀਆ ਸੈਮੀਨਾਰ, API ਸਕੋਰ, ਆਪਣੇ ਪੁਰਾਣੇ ਲੈਣ ਵਾਸਤੇ ਸਰਟੀਫਿਕੇਟ ਲੈਣ, ਔਰ ਇੱਕ ਬੜਾ ਵੱਡਾ ਡਿਵੈਲਪ ਹੋ ਗਿਆ ਮਾਫੀਆ, ਜਿਹੜਾ ਤੁਹਾਨੂੰ ਇਸ ਪਾਸੇ ਪ੍ਰਮੋਟ ਕਰਦਾ ਹੈ। ਤੁਹਾਡਾ ਇੰਪੈਕਟ ਫੈਕਟਰ ਕਿਵੇਂ ਵਧੇਗਾ, ਤੁਹਾਡੀ ਸਾਈਟੇਸ਼ਨ ਕਿਵੇਂ ਵਧਣਗੀਆਂ, ਤੁਸੀਂ, ਔਰ ਸਾਰੀ ਦਿਹਾੜੀ ਸਾਡੇ ਮਨ 'ਚ ਇੱਕੋ ਪ੍ਰੈਸ਼ਰ ਰਹਿੰਦਾ ਹੈ ਕਿ ਕੰਪੈਰੀਜ਼ਨ ਫਿਰ ਹੋ ਜਾਂਦਾ ਵੀ ਉਹ ਮੈਂ ਪ੍ਰੋਫੈਸਰ ਬਣ ਗਿਆ, ਦੂਜਾ ਰਹਿ ਗਿਆ। ਮਤਲਬ ਮੈਨੂੰ ਲੱਗਦਾ ਸਾਇੰਸ ਦੀ ਇਹ ਦਿਸ਼ਾ ਨਹੀਂ ਹੋਣੀ। ਹਾਂ, ਉਹਦਾ ਕ੍ਰਾਈਟੇਰੀਆ ਕੁਝ ਹੋ ਸਕਦੇ ਆ, ਦੇਖੋ ਇਹ ਤਾਂ ਨਹੀਂ ਕਹਿ ਸਕਦੇ ਜਿਹੜਾ ਜੌਬ ਕੀਤਾ ਉਹਨੂੰ, ਉਹ ਨੰਬਰ ਆਫ ਈਅਰਸ ਉਹਦੇ ਇਨਵੈਂਸ਼ਨ ਉਹ ਕਰ ਲਓ, ਕੁਝ ਸਿੰਪਲੀਫਾਈ ਕਰ ਲਓ। ਇਹ ਬਹੁਤ ਡੇਂਜਰਸ ਹੈ। ਔਰ ਐਸੇ ਪਿੱਛੇ ਕੀ ਹੁੰਦਾ, ਫਿਰ ਅਸੀਂ ਸੁਸਾਇਟੀ ਤੋਂ ਕੱਟ ਜਾਂਦੇ ਹਾਂ। ਅਸੀਂ ਆਪਣੇ ਕੈਰੀਅਰ ਵੀ, ਮੇਰੀ ਜ਼ਿੰਮੇਵਾਰੀ, ਮੈਂ ਜੇ ਪੋਜੀਸ਼ਨ ਲੈਣੀ ਹੈ ਤੇ ਮੇਰਾ ਇੰਨਾ ਇੰਪੈਕਟ ਫੈਕਟਰ ਹੋਣਾ ਚਾਹੀਦਾ, ਮੇਰਾ ਫਲਾਣਾ ਹੋਣਾ ਚਾਹੀਦਾ, ਮੈਂ ਇੰਨੇ PhD ਕਰਾਏ ਹੋਣੇ ਚਾਹੀਦੇ। ਅਰੇ ਇਹ ਤਾਂ ਕੋਈ ਟਾਈਮ ਬਾਉਂਡ ਥੋੜਾ ਹੈ। ਇਹਦੇ ਤੁਹਾਡੇ ਇਨੋਵੇਸ਼ਨ ਕਿਹੜੀ ਹੈ, ਕਿਹੜਾ ਤੁਸੀਂ ਟਾਈਮ ਲਾਉਂਦੇ ਹੋ। ਵਿਗਿਆਨਿਕ ਤੇ ਜਿਹਨੂੰ ਕਹਿੰਦੇ ਭੁੱਲ ਹੀ ਜਾਂਦੇ ਹੁੰਦੇ ਸੀ ਕੰਮ ਕਰਦੇ ਕਰਦੇ। ਸੋ ਕੈਰੀਅਰ ਕੌਨਸ਼ੀਅਸ ਜ਼ਰੂਰ ਹੋਈਏ, ਕੈਰੀਅਰ ਬਣਾਈਏ, ਬਟ ਇਸ ਤਰ੍ਹਾਂ ਦਾ ਨਾ ਬਣਾਈਏ ਵੀ ਮੈਂ ਸੁਸਾਇਟੀ ਨੂੰ ਪਿੱਛੇ ਛੱਡ ਦੇਵਾਂ, ਵਿਗਿਆਨ ਠੀਕ ਨਾ ਕਰ ਸਕਾਂ, ਔਰ ਸੈਲਫ ਹੀ ਹੋ ਜਾਵਾਂ। ਠੀਕ ਹੈ ਨਾ, ਕਹਿਣ ਨੂੰ ਸਾਰੀਆਂ ਅਸੀਂ ਲਿਖਦੇ ਹਾਂ ਆਪਣੇ ਪੇਪਰਾਂ 'ਚ ਵੀ ਇਹ ਸੁਸਾਇਟੀ ਦੇ ਕੰਮ ਆਏਗੀ, ਇਹ ਚੀਜ਼ ਕੰਮ ਆਏਗੀ, ਪਰ ਪ੍ਰੈਕਟੀਕਲੀ ਮੈਂ ਦੱਸਿਆ ਵੀ ਕਿੰਨਾ ਕੰਮ ਆ ਰਿਹਾ ਔਰ ਕਿੰਨਾ ਇਨਵਾਇਰਨਮੈਂਟ ਦਾ ਨੁਕਸਾਨ ਹੋ ਰਿਹਾ। ਸੋ ਇਹ ਕੁਝ ਗੱਲਾਂ ਮੇਰੇ ਧਿਆਨ 'ਚ ਸੀ ਜੀ, ਮੈਨੂੰ ਲੱਗਾ ਵੀ ਸਾਰੇ ਨਾਲ ਸ਼ੇਅਰ ਕਰਾਂ। ਜੇ ਕੋਈ ਹੋਰ ਪ੍ਰਸ਼ਨ ਹੋਵੇ, ਕਾਫੀ ਟਾਈਮ ਮੈਂ ਲੈ ਲਿਆ, ਬਾਠ ਸਾਹਿਬ ਦਾ, ਚੇਅਰਮੈਨ ਸਾਹਿਬ ਦਾ, ਬਾਕੀ ਆਰਗੇਨਾਈਜ਼ਰਸ ਦਾ, ਔਰ ਸਾਰੇ ਲਿਸਨਰਸ ਦਾ ਬਹੁਤ ਬਹੁਤ ਧੰਨਵਾਦ। ਥੈਂਕ ਯੂ ਵੈਰੀ ਮਚ ਜੀ। ਸਤਿ ਸ਼੍ਰੀ ਅਕਾਲ।
Thank you very much, sir, for this eye-awakening lecture. Thank you, sir, for gracing our occasion. Thank you very much, sir. Now, I will like to call upon the chairperson of the session, Dr. Kulbir Singh Bath, for concluding the session.
Thank you very much, everyone. Am I audible?
Yes, sir.
Okay. Thank you so much for making this session wonderful. We had some very good presentations by Dr. Narinder Singh, Dr. Arvind Kumar Gupta, Dr. Pushpinder Pal, Dr. Yashveer Singh from IIT Ropar. I don't have to say much because they are all good researchers. And lastly, we had a great lecture from Dr. Adarsh Pal. He talked about history of science and how the scientific tradition of the country that should be promoted. So in this regard, I wish to thank the organizers for conducting this session. It was very useful. And as everybody said that science, it should be sustainable. This is what the theme of National Science Day is also there. So Dr. Adarsh Pal, he was very much right when he said that we need to promote our traditions of science and technology. We had some great scientists, very good inventions and discoveries, but somehow we couldn't promote them. We couldn't tell to the world that they are our inventions. So the need of the hour is that ਜਿਹੜੇ अपने यहाँ के साइंटिस्ट हैं अब उनको unearth करना चाहिए whatever scientific discoveries and traditions we had that needs to be promoted. I wish to tell that Punjab State Council for Science and Technology, we had conducted a survey and then we got up and documented the history of science and technology in Punjab. So if it is available with the Punjab State Council for Science and Technology, I wish that everybody should go through it. There are also discoveries and inventions of Indian scientists from Punjab region in that document. And as Dr. Adarsh Pal rightly said, that we need to promote traditional science and technology, our own science and technology. And for that purpose also, we are coming up with a very good week-long festival that is known as Vigyan Sarvatra Pujayate. That is, science is revered everywhere. This is a great initiative with Vigyan Prasar, and we are doing it in 5 locations in Punjab and Chandigarh with the help of Vigyan Prasar. In that particular Science Week, we have sessions on annals of history of science and then Swadeshi Paramparic inventions and discoveries. So I wish that everybody should join that festival and celebrate science and traditional science and technology, what we have, what were our achievements, where we excelled, and what needs to be brought out. So with that, I thank you, all the speakers, all the organizers, especially Dr. Adarsh Pal. He has always been very, very excellent when it comes to talking about traditional science and technology. And he's a revered speaker, not only for us, for the whole state as well. Thank you, sir. And with that, I thank you. Thanks, everybody.
ਇੱਕ ਗੱਲ ਜੇ ਅਸੀਂ ਅੱਜ ਪ੍ਰਣ ਕਰ ਲਈਏ ਕਿ ਅੱਗੇ ਤੋਂ ਜੇ ਸਟੇਟ ਕੌਂਸਲ ਜਾਂ ਪੰਜਾਬ ਸਾਇੰਸ ਕਾਂਗਰਸ ਇਹ ਪੰਜਾਬੀ ਦੇ ਵੀ ਵਿਸ਼ੇ ਨੂੰ ਲੈ ਕੇ ਔਰ ਆਪਣੀ ਮਾਂ ਬੋਲੀ ਚ ਜੇ ਅਸੀਂ ਚਲਾਓ ਕਰੀਏ ਤੇ ਮੈਨੂੰ ਲੱਗਦਾ
ਬਿਲਕੁਲ I wish to add that we are also shortly going to begin one scope project which means science communication in local language. So we will join hand with you also, sir, in that particular project. Thank you. Thank you, everyone.
Thank you very much, sir, for concluding remarks. Thank you, sir. Now, to present vote of thanks, I will call upon Dr. Mandeep Kaur, Organizing Secretary, Punjab Science Congress 2022. Ma'am, please.
Thank you, ma'am, for giving me this opportunity to present my vote of thanks to all of you. I, Dr. Mandeep Kaur, on behalf of Shri Guru Tegh Bahadur Khalsa College, Shri Anandpur Sahib, extends a very hearty vote of thanks to all of you present now. As we end today's morning session, I would like to thank you all for joining the today's morning session. I express my sincere gratitude to the speakers for sharing their expertise with us. First of all, I must mention our deep sense of appreciation for Dr. K.S. Bhatt, Joint Director, PSC-ST, Chairman of today's morning session, for giving his valuable time to us. Further, we are grateful to Dr. Narinder Singh, IIT Ropar, for demonstrating his lecture on potential for nanomaterials for chemosensor development and water purification. I may like to express our sincere thanks to Dr. Arvind Gupta, IIT Ropar, for his analysis on modeling of non-equilibrium stochastic transport. I also wish to express my gratitude to Dr. Pushpinder Pal Singh from IIT Ropar for exposing the state of agriculture in India and possible technological interventions for evergreen revolution. I am also grateful to Dr. Yashveer Singh from IIT Ropar for explaining the role of chemistry for sustainable development. And at last, we also would like to acknowledge our gratitude to Dr. Adarsh Pal Vij, Chairman of Punjab Pollution Control Board, for giving his Desh Bhagat Singh Lal Singh oration lecture. It was a great, excellent lecture given by you, sir. We all are inspired by great lectures by today's eminent experts. At last, I thank you, all of you, from the core of my heart for being with us this morning session. Now I request all of you to have a break of 5 minutes. After 5 minutes, you all are requested to join the respective technical sessions that are going to start at 1 p.m. Once again, thank you, all of you.
Thank you, ma'am. At the end, I would like to extend my generous thanks to the chairperson, sir, our invited speakers, and all the participants who have cooperated for the successful completion of the session. Thank you very much. Thank you, everyone.